Hi guys, my name is Untitled and welcome to my Machine Learning Primer course. Whether you're looking to build out your actual machine learning skills or you want to see how machine learning can impact your organization, this is the right place for you. The first 4 chapters will have information for everyone. Chapter 5 onwards, we'll actually talk about implementing machine learning algorithms and we'll be writing real code. So if you're not interested in that, just stay until chapter 4 and you'll get all the information that you need. Machine learning is an ever-evolving subject, and there are an infinite number of things to learn, and it has a constantly evolving body of knowledge. And the purpose of this course is to give you a practical understanding of the basics of machine learning so that you can decide if this material is right or what material is right for you, and then focus your learning in that direction. For example, you might be more interested in boosting algorithms or neural networks. The background knowledge necessary for each of those is different. And I want this course to kind of give you just the basics you need in order to implement these things in a practical corporate environment. We won't focus too much on the math or the theory behind different algorithms. If you're actually interested in learning more about that, then feel free to check out the book Hands-on Machine Learning with Scikit-Learn, Keras, and TensorFlow, the 2nd edition. And I have an affiliate link linked below in the description or in the Notion notes if you're looking with those notes right now. And it's an amazing book, and it's what I use to get a deeper understanding of the actual algorithms and how they actually work at the core level. So before we get started, I would like to say, I'd like to give a chance to thank this channel's first real sponsor, DeepNote. DeepNote is an online notebook, like a Jupyter notebook, that makes it easier for you and your team to collaborate on data projects from end to end. I'll actually be running the code in this video through DeepNote so you guys can see how it works, starting from chapter 5 onwards, and y'all will see how well this tool actually works. And thanks again so much for DeepNote for bringing this course to life. All right, so let's get right into it. So I want to show you guys machine learning. It's always touted as this incredibly complex, very detailed subject. But I want to show you these days just how easy it is to implement machine learning in your organization. We're going to be writing an algorithm that works in just 4 lines of code. So it's actually going to be more like 6 or 7 lines of code, but 2 or 3 of those lines are just me importing stuff into my Python editor. So I wouldn't actually count those. So let's go ahead and get started. So we will switch to my screen. And I will open up a new notebook in DeepNote. So we'll just call this chapter 1. All right. And if you're at all interested in following along, check out the description below. You can use my affiliate link to join DeepNote, which is another great way to support this channel by showing them that I can actually push traffic to products if people like them. And let's go ahead and get started. So we just need to go and do a quick install. There we go. Actually, you know what? Let's just go ahead and copy this and then we will paste it in here. And I think we'll just run it as is. So what happens is because this is an online notebook and you're running it on the cloud, it actually needs to start up the hardware first. And after it starts up the hardware, then you're using hardware that's presumably nicer than the one you have on your laptop, actually. So the first thing we're doing over here is we're installing a library called PyCaret. PyCaret is a end-to-end machine learning library that was created, I forgot by who, but it's an amazing library, and we actually use it like at the company I work for to run machine learning programs from like end to end, everything from data cleaning all the way to actual deployment of the algorithms. So you can see we're just installing PyCaret right now. And then we're getting a data set over here. Again, I would say this line doesn't really count either because there's no actual logic over there. Whoops. Let us copy this over here. And now we're importing the regression module from PyCaret. Again, if you're not into the technical stuff, don't worry too much about this. It's actually a lot simpler than it looks. And we're going to be running a XGBoost model on this, which is, again, a bit more of an advanced model. So it's not like your linear regressions and stuff. It's a boosting algorithm, which have become quite popular in the last couple of years for all the Kaggle competitions they're winning. For anyone that's not aware, Kaggle is basically a website owned by Google where companies can post data sets online and run a data science competition where people can win real money by creating algorithms that perform the best in the competition that company has set forward. So boosting algorithms have become quite popular on that website and are kind of like the bread and butter of what people use in Kaggle because they're a combination of lightweight and quite powerful. They have amazing predictive power. Neural networks used to be the big thing. Boosting algorithms are kind of like what everyone's into right now. And it shows you just how fast the world is moving in the world of machine learning, which is why in this course I want to focus kind of on the basics, the stuff that probably isn't going to be changing anytime soon. So you'll see right now we're just installing a bunch of stuff. And of course, that's just because an end-to-end library is going to be quite detailed. All right, I think about 2 minutes into execution. All right, and there we go. It took about 2 to 3 minutes to run that. And basically, this is a data set where we have a bunch of information on, I believe, diamonds. And we want to decide how to price different diamonds. We're trying to predict pricing, basically. And we were able to create an algorithm that's able to predict pricing. And not only that, it tells us what is the most important feature, which is basically which variable is most important in determining the price of diamonds. So as you can tell, carat weight is obviously the most important. Now, with such a simple data set, you probably could have told me that yourself, but now we've mathematically proven it. So this is just a quick overview of how simple machine learning can be to implement. Now, obviously, if you were to actually do this for a company project or something, you would want to be a lot more detailed. You'd want to have a lot much more detailed notes as to how you actually did it. And you would probably do a lot of tuning to make sure your algorithm was more accurate. But I mean, this is where machine learning has developed to today. It's gotten so far that there are free libraries. This is a completely free library that allow you to end-to-end produce a machine learning algorithm, like in a real advanced machine learning algorithm in what is basically 4 lines of code. So that's just to show you guys how easy it can be. Now let's go ahead and talk about what machine learning actually is and go over the basics of machine learning. So machine learning is the study of computer algorithms that can improve automatically through experience and by the use of data. So what does that mean? It basically means that it's an algorithm that is deployed, and what it does is as more data comes to it, as it's given more data, more information, it can improve upon itself. That's the learning part of it. The machine is learning, basically. So let's think about it from the perspective of a problem. What is machine learning, and how is it different from, say, traditional programming or traditional software development? So let's say I work at Nike and I'm in charge of building a section of their website. When I go through their website and I scroll over different menus, they'll behave differently, but deterministically, which basically means that if I input a certain command, so say I hover over something, then a definite outcome will occur. So, let's just demonstrate this real fast. I'm using a new keyboard, but you see we're on the Nike website right now, right? And if I hover over these menus, then it deterministically will show me different options, right? Like this doesn't change. This isn't probabilistic or anything. And this is something that traditional software development is very well equipped for. But let's say the problem is now how to predict which shoes to stock in a location based on a bunch of customer data in that region. So let's say you have 10,000 dimensions of customer data, everything from gender to Instagram likes to favorite sports to average household income, stuff like that. If I wanted to use all that information to predict, okay, which regions of the country need which shoes stocked where, basically, more advanced inventory management, that would more or less be impossible to actually program. It would be impossible for me to take these 10,000 different dimensions and then have rules basically as to, okay, if you see this gender in this region, that, all of this information, put this shoe over there at this level of safety stock. We might be able to do that for 30 stores or so, but what happens when the data changes or we need to roll this out nationally? The hard-coded solution is not at all scalable, and instead we would use a machine learning algorithm to ingest all of that data, the 10,000 different dimensions on all the different customers that we have, and produce a prediction based on the result of maybe 10 hard-coded stores. So what happens is you would say, okay, given these dimensions, we know that these demographics like these types of shoes, and we'll put them in these stores, and then you feed that to the machine learning algorithm, and then it's able to learn that, and sometimes it's able to even create its own different predictions based on that data. So essentially, a machine learning algorithm takes a bunch of inputs in the form of data and then produces an output that maximizes some target metric, in this case, maybe user retention, user happiness, etc., and it can improve itself through more data being added to the algorithm. Another great example would be your Spotify playlist. There is no way to hard code a good recommendation algorithm for the millions, if not hundreds of millions of customers that Spotify has. How do you recommend good music to hundreds of millions of unique customers? Well, you can't really hard code that. At least, if you hard code it, you're going to have a heuristic rules-based engine, which is not going to be as detailed as it needs to be for everyone's individual taste. And that's where you would throw a machine learning algorithm at it and say, okay, Given that we've hard coded this for 1,000 customers, go ahead and start figuring out, okay, what is Shashank like? And if he listens to XYZ music, where is he going to go from there? And continuously improve. That's another big thing. Machine learning algorithms can continuously improve and get better and better, provided you set certain parameters with them. So that's where machine learning is very different from traditional programming. So machine learning in business, right? Machine learning is already used in all aspects of business. And for any business that's looking to get closer to their customers or to improve decision making. Spotify, YouTube, Netflix, these are companies and other tech-first media companies will use machine learning algorithms to help improve recommendations for their customers. What song should you listen to next? What artist should be suggested? This is all decided based on a series of parameters that data scientists and machine learning engineers are able to figure out by using hundreds of billions of rows of data from hundreds of millions of customers. Spotify, for example, has figured out that the magic number as to whether you like a song or not is they can decide at around 30 seconds of listening. Once you skip a song within the first 30 seconds, they're like, okay, they probably don't like this type of music. This was back in 2015, so I'm not sure how accurate this is today. But that's the thing. It's a constantly evolving and constantly improving field. Another great example is on Netflix. You might notice that on your Netflix account versus someone else's Netflix account, the actual screenshot that shows for different media that you want to watch, for different videos you might want to watch, is different for you versus someone else. So for example, if you have a significant other of a different gender than yourself, it's a lot more obvious. Men and women get shown very different screenshots when looking at the same media. And Netflix is able to figure this out based on, they're able to figure out your gender and then be like, okay, male viewers of this demographic generally like to see this screenshot versus female viewers of this demographic generally like to see this screenshot. And if we show them this screenshot, then it'll get them to view the video, which is exactly what they're trying to maximize. They're trying to maximize the amount of time you spend on Netflix's site. It's like Reed Hastings, the CEO of Netflix, said, Netflix's biggest competitor is not YouTube or anything, it's time and it's sleep. So Nordstrom, the company I currently work for, is a major North American fashion retailer and uses machine learning to assist our digital stylists in helping customers with their fit. So basically what happens is we'll use AI and convolutional neural networks, and there's a great article over here written on the Nordstrom Tech blog, where they use AI in order to help create outfits for different customers, and then a professional stylist will come in and then make minor tweaks to it. And that's kind of where you'll see if you want to implement machine learning in your organization, that's kind of the direction we're going in. In the year 2015, around that time, people were really hyped about AI, machine learning doing absolutely everything. But it turns out that you can't do everything with machine learning. Machine learning plus the human connection are what can create really natural looking and natural sounding recommendations for your customers. And that's why you don't want to just replace people with machine learning algorithms. We are not at a level of advancement where we can do that for a lot of professions. You want to combine machine learning with human intuition and use the machine learning and neural networks to really kind of make a cyborg out of people and help them extend themselves and move a lot faster. Machine learning is not there to replace people in all cases. It's there to augment people. That's the word. It's there to augment people and make them better and more and faster at their jobs. And Stitch Fix is another great company where they kind of realized this too, where they went from the fully algorithmic approach to an algorithmic plus human approach to their styling recommendations. So the next question you probably have is, how do you know when to use machine learning? So machine learning is a tool, and like any tool, like a hammer, like a screwdriver, it should only be used in situations it's best equipped to handle. You don't want to use a hammer to screw in a screw. These are software solutions where coding the rules by which the software should work is too cumbersome and can't be scaled. So there are two major solutions, or there are two major problem types where you would actually start using machine learning. One is a problem type where you cannot code the rules. This is kind of like our Nike example from earlier. And this includes things like facial recognition or voice recognition, where very subtle differences between individual features on a face and voices can render a rules-based approach unusable. Ask yourself, for example, if I wanted to code a facial recognition algorithm, how would I actually code that? Maybe you could get basic things like skin tone and other things working, but then what happens when, for example, it's shown in a different light? What happens when, for example, you put on glasses? This is stuff that machine learning algorithms are great at learning, but a rules-based approach would not do a great job in actually coding. You would have a very difficult time coding that, basically. The second type of problem where machine learning makes the most sense is a problem where you cannot scale. And this includes things like the previous Nike example, and where there are thousands of variables that you need to consider. It might not be possible or economical to hard code rules, and machine learning might be necessary. And there's a great link over here that I have in the Notion page where you can, when to use machine learning. AWS has a great article on, expanding on when you should be using machine learning. And these Notion notes are obviously available, link in the description below. So machine learning might also be a great V2, version 2, for a product that you're creating. If you wanted to create a stock trading bot, for example, that traded stocks based on whether the president of the United States mentioned them positively or negatively in a tweet, then you could start with a simple version that just counts the number of positive words in a tweet. And then you could start with it counts the positive number of words in a tweet versus the number of negative words in a tweet, and then makes a decision based on that. Of course, this approach will quickly fail, as there are many quirks of grammar where you can use a negative word and the sentence is still overall positive. And that's where you might want to then put in a sentiment analysis bot that actually uses natural language processing to actually understand the sentiment of the sentence being said. And I said this because there was a very funny video I watched a couple of years ago where, when Trump was president, obviously the guy was very tweet happy. Someone actually coded a bot that would trade stocks based on whether he spoke about a company positively or negatively in a tweet. And the bot actually ended up making a decent amount of money and beating the market very slightly. So that's another way if you actually want to implement machine learning in your company. You might want to start off with a version 1 that is a rules-based approach, a regular software development approach, and then implement machine learning as a V2. But I would also say, given how easy machine learning can be to implement these days, maybe you just go straight for the V2. So that's just to give you a quick overview of when you can implement machine learning. The next question, something I want to bring up is ethics in machine learning. So ethics in AI and ethics in machine learning are topics that are of great importance today, and for a very important reason. So, let's go story time. The Code of Hammurabi were a series of laws from the ancient civilization of Babylonia. There were about 300 laws, and there were 300 laws written which talk about how all aspects of ancient life were to be governed. And the full text is linked below. And Law 229 is something that really caught my attention. If a builder builds a house for a man and does not make its construction sound, and the house which he built has collapsed and causes the death of the owner of the house, the builder shall be put to death. Now, basically what this is saying is that that creators should be responsible for the soundness of the work in which they create. Now, for better or worse, we don't actually have laws that are quite this strict. People are usually not put to death over the soundness of the construction that they build. But machine learning algorithms have become so ubiquitous, and they form such a large portion, if not a majority of, for example, the trading volume in stock markets, that I think it's important that software engineers, machine learning engineers, and data scientists hold themselves to an ethical standard to the algorithms that they create. So, for example, a doctor, medical malpractice is something that all doctors fear, and they have insurance to prevent such medical malpractice. But software engineers may not be held to such a high standard of the ethics of the algorithms in which they create. A lot of it just having to do with the fact that you maybe need a dozen software engineers to make one thing, and it's where do you actually put the blame on that? And a concrete example of this is, for example, Amazon's facial recognition algorithm called Recognition, which was, it falsely mismatched 28 members of Congress with criminals from I think the National Criminal Database or something like that. And it disproportionately matches people of color to criminals, which is a problem most likely with the training data set used to actually train the algorithm. Now, Amazon has pulled the algorithm away and said they're not going to sell it to police departments or anything. But the point I'm making is their machine learning algorithms, especially the engineer type of person, right? They love creating things. And it's important to also consider the ethical ramifications of the things that you're creating. And unlike, for example, lawyers or doctors, software engineers and developers are not necessarily held institutionally to the same ethical standards. There's no Hippocratic oath that anyone takes when they join corporate America as a software developer, as a machine learning engineer. And that's why I want to communicate in this course that this is something that's important to consider whenever using machine learning in your algorithms, because you're not hard coding the rules. You have to predict kind of what your algorithm will be doing and what are the ramifications of what your algorithm will be doing. I will not say I'm at all an expert on the ethics of AI, but it's just something I want to make sure that people are cognizant of whenever they are learning about the subject. All right, so now let's go to the theory behind machine learning. So how to holistically design a machine learning algorithm using CRISP-DM. So I'm a very big picture guy, and I firmly believe that you always need to keep a firm eye on the greater impact of your work in order to drive real value within your corporation. With the ease by which we can deploy machine learning algorithms these days, it's important to understand that machine learning projects are only useful insofar as they solve some real world purpose. I don't want to teach you to just throw a machine learning algorithm at a problem and hope it works. To this end, we'll be using a framework developed by IBM in the 1990s called CRISP-DM. They've updated it, but I find CRISP-DM to be a tremendous framework that works quite well. It's basically a cycle we can use to map the life cycle of many data center projects, and it's what I use for almost all of the my data projects in my daily life, from my consulting to my regular day job to, even sometimes what I do on YouTube. And CRISP-DM is basically an acronym, and it stands for Cross-Industry Standard Process for Data Mining. I should probably put that over here. Cross-Industry Standard Process for Data Mining. And the different steps of CRISP-DM start off with business understanding, data pre-processing, modeling, evaluation, and deployment. Deployment will be a little bit out of scope for this course. So it'll be a cycle that looks just like this. And basically, you'll see that you start off with business understanding, and there's this arrow going back and forth between business understanding and data understanding. And I like to say business understanding is kind of where projects live, they live and die at this stage, where basically you're trying to understand what is the actual problem you want to solve. So we'll go over that in a second. So business understanding and data understanding. The first step of this process, and it's where I like to say this is where a lot of machine learning projects stall out without anyone really knowing so. When we talk about business understanding, we're referring to the process by which, as the data expert, you sit down and understand the scope of the problem, define the objectives, and then check to see if you have the data necessary to accomplish it. Checking to see if you have the data necessary to accomplish it, that's called data understanding. Because oftentimes, and the reason this whole process, the reason that data science jobs haven't been fully automated is because half the time we just don't have the data necessary to actually solve a problem using machine learning or AI, and that's kind of where getting a hold of that data is, that's half the struggle there. So remember, you'll almost never be asked to directly build a machine learning algorithm. Almost no one will ever go to you and say, the business objective is to build a machine learning algorithm. Remember, it's just a tool. The business objective is going to be something, and machine learning will just be a tool in that business objective. I have a lot of people ask me, what skills do I need to learn in order to get a job as a data analyst? And it's a difficult question to answer because a lot of it just depends on what level of advancement your company is in its analytics journey, and that will determine what tools make the most sense for your company to use. And that's why I like to really hammer home the point, understand the business objective, understand what stakeholders actually need done, and see if machine learning fits in that framework, and if machine learning is the best solution for that framework. Maybe something a lot simpler is what you really need to be doing, or maybe you need to bring in outside counsel. So for example, there are data science firms that specifically are experts at deploying machine learning algorithms to deploy a particularly advanced algorithm for your organization. At the end of the day, the business understanding, data understanding step of CRISP-DM is key to a successful machine learning project being implemented. You'll notice that there are arrows going back and forth between business understanding and data understanding. And this is because people might request that you try and solve a problem with data that you don't actually have the data to solve. And this is why the back and forth understanding between your business objectives and your data objectives and your data capabilities are quite important. And in order to keep this course a bit more focused on the machine learning, I'm going to skip over this section of the process, but I'll have a full video in the future where I go over how you actually ask stakeholders, what questions you ask, what are the probing questions you ask, how do you actually determine what do you guys need done, and how do we dig into that and make sure that we actually understand that. You'll have certain stakeholders that are very good at defining their objectives, and you'll have other stakeholders who are not quite good at that. And as a data expert or the leader of a data team, it's your job, because you're the implementer here, to make sure you get those requirements in writing and agreed upon by all parties. The next step of the cycle is data preparation. And data cleaning can be a tedious process, but it is one of the most important, if not the most important step of the machine learning process. There's a saying in the data science community, garbage in, garbage out, or GIGO. Preparing your data serves three major functions. It translates all of your data into a format that the machine learning algorithm can work with. A lot of machine learning algorithms only work with numerical data. So say, for example, you have names, or you have flower types, for example. You need to encode that into some numerical format. And we'll be going over how to do that in this course. It cleans up junk or meaningless values from your data set so you don't confuse your algorithm. Oftentimes you'll have missing data, or you'll have junk data that doesn't really mean anything. And you want to make sure you get rid of that. That way your machine learning algorithm can learn appropriately. Remember, your machine learning algorithm is kind of, the way I like to say, think about it is that It's a room of 1 billion 4-year-olds. There's not a lot of intelligence in there, but they can add 1 + 1 and get 2. And it's up to you to set up the problem such that your billion, 4-year-olds can do very simple calculations and come up with actual insights. But at the end of the day, you need to set up the correct learning environment for these 5-year-olds or 3-year-olds, I forget which age I picked, to actually learn well. They can't learn on their own. The environment has to be set up for them, but they can do basic arithmetic on their own. And when we go into the actual implementation of these algorithms, you'll kind of see what I mean by this with this analogy of like a room full of 5-year-olds, which is really what machine learning algorithms are. And finally, it can add new information to your data set that so that your algorithm can derive better insights. So this is what we call feature engineering. And this is basically using domain knowledge to enhance the ability or enhance the quality of your data. So for example, say you work with automobiles, right? Using a bunch of like random information, you can put together engine displacement, which is basically just a measure of how much fuel an engine uses per cycle that it runs. And it's a major determinant of the power output of an engine. So that could be another feature you could add that you kind of like put together in a column. That way your machine learning algorithm doesn't have to figure it out itself. And it's able to use displacement to figure out maybe the cost of a car. Generally higher displacement engines, especially in today's eco-conscious world, cost a lot more. Back in the 70s and stuff, cars used to be way higher displacement, way less efficient, more like the 60s and early 70s. And today, because of all the environmental regulations we have for good reason, higher displacement engines tend to be a lot more expensive because you have to have all kinds of computer algorithms in there to make sure that they actually like meet emission standards. So although jumping straight into modeling is very tempting, your algorithm's performance will be largely dependent on how well you've been able to clean your data. So don't skimp on this step. One more thing that we'll want to do in the data preparation step is to split our data into a training data set and a testing data set. So you'll have a bunch of data, right? And you want to split it to where about 75 to 80% of your data is what you call a training data set. And this is what you actually train your machine learning algorithm on. It doesn't see the testing data set, which is that 25 to 20% or that 20 to 25% of data that you like split away. And what happens is after you train your machine learning algorithm on this training data set, then you go and you test it on your testing data set to see what's the actual performance on data it's never seen before. And it's really important that the algorithm never actually sees this testing data set. That way you can get an actual gauge of the performance of your algorithm. One more thing I want to say that I haven't written down over here is that the process of data cleaning and data preparation can take up about 80% of your time or your effort because data is almost never in a clean enough format to just be thrown at a machine learning algorithm. So one thing that you may have noticed with that 4 lines of code in order to get a machine learning algorithm, I did no data preparation in that because the data was already pre-prepared. That was kind of the way I cheated it into being able to do it in just 4 lines. But in real life, data is almost never fully prepared for you, and you have to prepare it prior to putting it into a machine learning algorithm. Again, these things are not intelligent enough to prepare data themselves. Now, people are making machine learning algorithms that'll prepare data, but they can be very finicky, and that's where data preparation is a very, very important step. I would say the modeling step is where a lot of the higher level math in data science comes in. That's kind of where a lot of the expertise comes in, but data preparation is where a lot of the effort goes. So it's like expertise versus effort, So the next step is modeling, and this is generally considered the most fun part of machine learning, and it's kind of like this is like the machine learning part of machine learning and like the data science part of data science, I like to think about data preparation as the meat and potatoes of XGBoost and modeling as the spices. You can't eat spices raw, but your meal won't taste that interesting without spices. So the way the way this comparison works is through just basic data preparation, you can actually get a lot of insights from it. With just meat and potatoes, you have a full meal over there, but it won't taste good until you add the spices. It won't be interesting until you add the modeling. So as you can probably tell, I like to use a lot of analogies. So modeling is where the rubber hits the road and where all the work we've done up until now shows. And modeling is kind of like where you'll see if you did a good job with all your preparation work. Did you meet with the business stakeholders and did you get the correct requirements? Did you actually prepare your data correctly? Do you actually have all the data you need to model? So if you do all of the steps prior to modeling thoroughly and accurately, then your modeling journey will be a lot more fun. And it'll just be a bunch of algorithms that you get to throw at a problem and fine tune. And this is kind of like where a lot of data scientists say they have a lot of fun with the job. whoops, got to finish that. All right, so determining which models to use. So chapter 4.3.1. The first step in the modeling section of the process is to determine what type of model we'll be using. There are three major paradigms of machine learning algorithms, each that has a couple of problem types. Let me put that over there. So you have the supervised paradigm, the unsupervised paradigm, and the reinforcement paradigm. And I will not be going over the bias variance trade-off. So supervised, this is the first paradigm and refers to a problem where we're trying to match a set of data to an expected set of outcomes. The expected set of outcomes is called our target variable, and is what we're trying to predict. The set of data and okay, so whoops. An example would be trying to classify images as hot dog or not hot dogs, given a bunch of labeled images of hot dogs that the algorithm can reference. So basically, what happens is if you have labeled data that the algorithm can reference and be like, okay, I want to match this with this, like all of this data, I want to match it with this thing, that's a supervised algorithm. So another great example is that diamond data set that we worked with at the beginning of the course, where basically what happened was I had the prices of every single diamond, and then I had all this information on like carat, weight, all this other stuff. And basically what the machine learning algorithm was doing is it was looking at all of these variables and it was looking at the price and trying to draw connections between the two. So when you have the target variable, I wanted to predict price. And when I have like a subset of prices that I can match my algorithm to, that's a supervised algorithm. Now, within the supervised paradigm of algorithms, you have regression problems and classification problems. So you have two different problem types. And a regression problem is one where the data we're matching to is numerical. So for example, price is numerical data, right? And so we'll be creating a regression algorithm to basically take a bunch of factors and predict a price based on that. And the way you prepare data and everything for a regression algorithm is going to be different than a classification problem. Classification is the second problem type in the supervised paradigm, and it basically is a type where you're trying to classify things into groups. So for example, a great example of this would be hot dog versus not hot dog. You're not predicting any numbers over here. You're basically trying to predict, given an image, is this thing a hot dog or is it not a hot dog? That's a classification problem. And that's specifically one called a binary classification problem because there's only two classes that something can belong to, hot dog or not hot dog. And that's different from, like, say, a multi-class classification problem where maybe you're trying to classify based on an image of a house, what type of house is this? Is it a duplex? Is it a townhome? Is it a condo? You know, stuff like that. That's a classification problem. The next paradigm is unsupervised learning. And this is basically the opposite of a supervised algorithm and refers to a problem where we don't have any labeled data and we're just telling the algorithm to try and find natural patterns in the data. In other words, we don't have a target variable. This would be like taking a bunch of customer data and telling an algorithm to find natural groups based on the data, and then we can discover patterns in that data. So this is a really interesting technique that is probably not used enough. And what you can do is you can basically take a bunch of customer data, right? And you can throw what's called a KNN algorithm on it, K nearest neighbors. And basically what it'll do, again, if configured correctly, is it will break this customer data into different subgroups. So for example, maybe you have business expertise that says that customers that live in Dallas, Texas tend to like the Toyota 4Runner more than customers that live in Denver, Colorado. But what happens is you can then throw a machine learning algorithm at it and it'll get a lot more specific. It'll be like, oh, customers in this city, in this state, or in this city, in this county, in this state, like this specific car, and the dealerships in that region should be stocked with this car versus something else. I mean, a great example would be if you just go around Texas, you'll know that people love pickup trucks over here. But what type of pickup truck do they like? Do they like the full-size pickup truck, like the Ford F-150, or do they like the mid-size, like the Ford Ranger? I mean, obviously it's the full size, but you know, a machine learning algorithm could prove that out for you. And this is where a clustering algorithm comes in. It will cluster your data into natural groups, and you can change different factors in your algorithm to basically make it create more or fewer groups. So basically, maybe if you tell it to create 10 groups, it creates these hyper-specific groups that are too specific. Someone who lives in a very specific section of a very specific city will like this thing, but you only have one dealership in that entire city. So what's the point of knowing that information? I want to know it at the city level, not the specific neighborhood within that city. And that's why you can use a clustering algorithm, and then you can increase or decrease the specificity of that algorithm, kind of make it increase the number of clusters or reduce the number of clusters, basically, so that it's not like creating clusters where there may not actually be any. And then finally, reinforcement learning. And reinforcement learning is a form of learning where the algorithm is asked to solve a problem and is rewarded for certain types of behavior and punished for other types of behavior. We will not be covering reinforcement learning in this course. And a great example of this is, for example, one way to teach, I think AlphaGo, the machine learning algorithm that beat Lee Sedol and became basically the world champion of Go. I think that's a reinforcement algorithm. Basically, you can play a bunch of games, and every time it does something, it loses or metrics are bad, you punish it and say that's bad. And every time it does good, you say that's good. And it just basically, it'll run like a million iterations of a game and finally figure out, it'll draw out patterns and be like, oh, okay, this is good and this is bad and this is how I should behave. Another example that definitely is like this is algorithms that teach software how to walk, for example. Instead of trying to program walking, you can throw a reinforcement algorithm at it, and then the algorithm will naturally actually figure out, if you give an algorithm a human body, basically, like 2 legs, 2 arms, a torso and a head, it will actually naturally start walking like a human, because that's the most efficient way to walk, and it figures that out through reinforcement algorithms. We never actually taught it how to walk. We never programmed anything. It just learns it by itself. I'll see if I can link something in here with the video I'm talking about specifically. Next, we have the implementation of the model, and we're still in the modeling part of CRISP-DM. After we cleaned our data, selected our model or the models that we'll use, we need to actually implement the model, and this is where we'll train our model. And training refers to the process by which we reveal our training data to the machine learning algorithm, and if it's a supervised algorithm, we try and match or fit it, fit is the correct word, to the target variable. And if it's an unsupervised algorithm, then we have it try and find patterns in the data by itself. After we've trained our model and taken some initial measurements, we might want to improve its performance through a process called hyperparameter tuning. What exactly are hyperparameters? So hyperparameters, to learn what hyperparameters, we'll take a quick look at how a machine learning algorithm actually works. A machine learning algorithm can be thought of as a complicated math equation with a bunch of different variables. This isn't strictly accurate, but works for the sake of our example. During training, our machine learning algorithm is trying out a bunch of different values for each of the variables in said equation until it's able to maximize some other equation called the cost function. Or usually it's trying to minimize the cost function. The values that it's changing are the parameters of the machine learning algorithm. Ergo, a hyperparameter is a value that is used to control the overall training process. Hyperparameter tuning is the process by which we iterate through multiple hyperparameters in order to create the best learning environment for a machine learning algorithm. And this is kind of where that whole analogy I had with the 5-year-old in the classroom goes. You want to create the best learning environment for your algorithm, and that learning environment is defined by your hyperparameters. That's hyperparameter tuning. So after you train your algorithm, you might do a little bit of hyperparameter optimization to try and figure out which hyperparameters make the most sense and work the best. And then finally, within our CRISP-DM framework, you have evaluation. And after training our algorithm, we'll want to determine how well it has performed. And to do this, we'll test out the performance of our algorithm on the test data set we separated from the rest of our training data set in the data preparation step of the process. This only applies to supervised learning because you're actually matching things together. You don't actually do this for unsupervised learning or reinforcement learning. We will then compare the predictive power of our machine learning algorithm on the training data set versus the test data set. And there are different measurements we'll use in order to determine how well our algorithm actually performs. The point of measuring the performance of our algorithm against a test data set is to simulate performance of the algorithm in the real world with a data set the algorithm has never seen before. We'll use different measures depending on whether we're working with a regression or classification problem. And I'll go over the details of each of these methods in the next chapter, chapter 6 basically, where we'll actually solve one of these or each of these problems. So with regression, you have these measures over here, and classification, you have these measures over here. This is basically how you determine how effective your algorithm actually is. And we'll go over them when we actually create these algorithms. And you might be asking yourself why it's so important to independently test the performance of our algorithms. And it's because machine learning algorithms often perform better when they're exposed to more data. So why are we purposefully preventing the algorithm from seeing a section of our data? Well, we want to do this to prevent something called overfitting. Overfitting is a phenomenon that occurs when a machine learning algorithm performs too well and matches to the data set it's trained on too well. And this is not good because an overfitted algorithm can't generalize and therefore won't be able to make predictions on data it hasn't seen before. Underfitting is the exact opposite and refers to the concept where an algorithm generalizes too much and can't give us anything near an accurate prediction. By removing some data in the form of our test dataset, we can compare the results of our test dataset to ensure we're not overfitting our data. Underfitting is prevented by tuning our hyperparameters and giving the dataset more, or giving the algorithm more data. So basically what happens over here is if an algorithm is overfitted, then what happens is it can't generalize and it can't actually predict on data it hasn't seen before. It's basically too good on the data it's trained, and whenever you show it new data, it has no idea what to do. And that's overfitted data. And underfitting is the exact opposite, where it generalizes too much. So what you actually want from your machine learning algorithm is you generally want it to actually be a little bit incorrect, because that means it's generalizing well. At the end of the day, these algorithms are not going to be perfect, and they're supposed to generalize. Obviously, depending on the context in which you're using these machine learning algorithms, the level of generalization will change drastically. So for example, for cancer diagnoses, you'll want a very different level of precision versus, for example, maybe inventory management. And we've actually reached a point where cancer diagnoses are more accurately performed by computers than by real humans. So by looking at MRIs, computers can more accurately tell if someone has cancer than a human can. So, I mean, there are a lot of professions out there in the world that algorithms are becoming better and better at doing than humans are, because they can take in an infinite amount of data, or well, a large amount of data, and accurately predict on that data. Another great thing, there's a great example of people think that art, for example, is a form of human work that machines can never do. But machines these days, using machine learning, can create real art. They can create paintings. They can create music that is impossible to differentiate from human beings. So, I mean, even art is a dimension where machine learning is taking over. Like this, machine learning is going to take over the world and is going to be widely implemented everywhere. And that's why I think it's important for everyone to have a basic understanding of how this stuff works. And the first 4 chapters that we went over, that's exactly what we did. So if you're not interested in actually implementing the algorithms yourself, thank you so much for joining. If you want to support this channel, feel free to like and subscribe to the video, like the video, subscribe to my channel, and feel free to donate to my Patreon if you're at all interested in seeing more videos like this. But if you're at all interested in seeing how we actually implement this stuff and you want to see how DeepNote actually works, let's go ahead and get started with Chapter 5. All right, welcome back, everyone. We are now in the application section of the course. This is the section where you'll be expected to code up your results. And if you don't know how to code in Python, don't worry. I have a free course linked below in the description below and linked in the Notion template right over here that has all the information that you'll need in order to be ready for the rest of this course. So if you don't know Python or you need a little bit of a refresher, be sure to check out my free course available over here. I also have a free SQL course on my channel and a free Tableau course. And I think I have like a stats course there too. So basically I have a lot of free courses. So be sure to check them out. All right, so normally I would run this on my local machine, but to simplify the process of getting off the ground, we're going to be using DeepNote, sponsor of today's video. If you want to get started, feel free to use my affiliate link below. I'll have a link in the description below as well. And by signing up for a free account using this affiliate link, you can also help me prove to future channel sponsors that people like the content that we're making here, so I can continue to make more courses like this. DeepNote basically provides an online Jupyter notebook with extra features like collaboration tools, easy integrations, and with other data sources, auto-saving, easy sharing, and GPUs if you need them. Once you've created an account, you can access the project with all of the code using the link in the description below. And this link over here, Machine Learning Fundamentals. And then once you sign up for an account and get it, then you can simply duplicate the notebook, pressing this duplicate button over here. So if you're going to use this, please click on the affiliate link and sign up through that. That way I can actually like prove, hey, like people actually, you know, listen, like the products that we have on this course. I mean, on this channel. So for this chapter, we're going to be working on data cleaning techniques. So that will be chapter 5. So let's go ahead and put this over here. Put this over here. And all right, we will start with chapter 5. I will create a new workbook. All right, so here's our new notebook. We're probably gonna have to use pandas. So we'll just import pandas as PD. and let the notebook hardware start up. So let's zoom in a bit over here. All right, so initial setup and import. So pandas is the standard library for tabular data manipulation in Python, and we'll be using that over here. So we're going to be implementing a couple of machine learning algorithms, and we're going to start off with the data cleaning process. So there are a series of common data cleaning procedures that are used with for setting up a lot of machine learning algorithms. So we're going to be going over the basic ones over here. There might be some that you might have to do in addition to this, but this should cover a lot of the basic data cleaning that you need for a machine learning algorithm. And what we're doing over here is I'm showing you the format that data generally has to be in order for you to put it into a machine learning algorithm. And then in chapter, I believe 6, we'll actually put it inside a machine learning algorithm and see how it works. All right, so we'll want to import the pandas library and then import our CSV and take a quick look using the .head method. So we import pandas as PD, and then let's also import NumPy. And then career data equals pd.read_CSV data career data.csv. There we go. And then let's take a quick look at it. And I just hit Shift Enter to execute the code cell. So we're going to be working with a Kaggle dataset that I modified slightly for the sake of this course. You can find the original Kaggle dataset over here, created by these guys, Prompt Cloud. So Kaggle has tons of great datasets that you can use to practice all kinds of processes you want to get better at. I believe this is a relatively large data set. That might be why it's taking a second to run. And a great feature in Deep Node is you can also turn on notifications. That way your browser notifies you whenever it's done executing on a cell. And you can go do something else in the meantime. All right. There we go. So it looks like we have quite a few rows of data. Quite a few columns of data. And basically what this is this is from some career website. It's basically just a bunch of job listings from a career website. So let's go ahead and first talk about the basic data format that you need in order to actually put data into a machine learning algorithm normally. So there are many different types of data. There are many different data types that data scientists work with. And for the sake of simplicity, we'll only focus on the normal tabular data types. So nothing like geospatial data or anything like that. And the basic format that the data going into a machine learning algorithm needs to follow is outlined below. Each column should represent a variable or feature of the data set. So we call them features in the data science world. And in this data set, it looks like we have 40 columns of data. That may or may not be accurate anymore. So I can figure that out by going career data.columns, and then we'll just take the length of this. So this method, or this just lists out all the columns of the data set, and by doing len, we can see how long it is. So there's actually 30. I removed a lot of the columns to reduce the size of the data. And then one or a set of columns should be what we're trying to predict. In this, I believe it is salary type, but we're not going to be worrying about that at this exact moment in our process. And then each row should represent a new observation for a certain column or combination of columns. There shouldn't be any duplicate rows, basically. You can have multiple values within one row, but you need to have some way to differentiate each row one after another. There shouldn't be any duplicate rows, really. And in this data set, the unique ID, unique spelled UNIQ, that is our unique row for each data set. So each column represents a variable and each row represents an observation. That's the basic format data has to be in for most machine learning algorithms for it to work well. So in the world of data science, we would refer to individual columns in a properly formatted data set as features or variables. You'll hear me using this term a lot more going forward. All right, so the first thing we want to do is we want to remove columns with only one unique value. So I generally try and remove, so for me personally, I generally try and remove as much data as possible from a data set as early as possible. And as you work with larger and larger data sets, you'll run into performance bottlenecks and time constraints unless you find a way to limit the amount of data you're actually working with. So this is this is an actual real problem I've encountered on many occasions where I'm asked to output an analysis relatively quickly, but each step takes a while to run, which is why it's very important that you limit the amount of data that you're working with as much as possible. To this end, we'll want to remove columns where there's only one unique value, as this means that this column has no predictive power. If every value is the same, then the machine learning algorithm won't be able to predict anything using these values. So for example, if we have a column that says flower type and every single flower is the exact same, that column can't be used to actually predict anything, and it has no predictive power. So we should just remove it right now. It's junk data, really. And we can determine the number of unique values in our data set using this line of code. Career data.nUnique. So let's go ahead and copy that. We'll paste that over there. And what happens is you get a list of every single column and the number of unique values in that column. So you'll see we have quite a few columns where it looks like it's just one value. And we want to get rid of these because it's just creating a performance bottleneck for our data. And it's just more stuff to look at. Again, I try to limit the data as much as I can. That way you can just focus on what's important. More data is generally better, but not all the time. So we can go ahead and do this using a simple little calculation I created. So what you do is you create a variable called columns to drop. And basically you take that same career data.nUnique method that we used earlier, and you limit it to anything where it equals 1, and then just find the index of that. So it'll output a series, and then you just get the index of that, and you'll get a list of columns to drop. So you'll see if I run this, job board, geo, job post, laying, inferred country, these are all columns with only one value, one unique value in them. So we're going to be dropping all of these columns. And then all we have to do is go ahead and drop the columns. Whoops. So you'll see over here, what I actually like to do personally is every time I do a new major step and I like modify the data substantially, if I have enough space in my system, then I'll create a new variable each time. That way, if I ever make a mistake or if I ever need to backtrack, I don't have to load in all of the data again and run every single cell one after another. I can go ahead and just run the previous 2 cells or something like that. And that's why we want to do career data dropped calls equals career data.copy. We're creating a copy of the data frame. And I'm going to drop, and then remember, you need this columns parameter. So you take that data frame dot drop, the columns parameter, and then we're going to drop this columns to drop variable over here. So we're going to remove any columns where we aren't getting any unique value out of it. So let us see how many values we've dropped. So it looks like we dropped 9 columns. That's pretty good. That's 1/3 of our data that we don't have to worry about anymore because it was adding no value. So, I mean, you know, depending on how much data was actually inside each of those columns, you may have dropped over 1/3 of the space that your system needs in order to compute all this stuff. So, awesome. That's step 1 of the data cleaning process. Get rid of any columns that aren't going to provide you with great data. So one thing to note is that this method doesn't drop columns where all the values are null, and we can do that using the drop NA method. So null data is also another type of data that isn't particularly useful in the context of a machine learning algorithm. So what we're going to do is we're going to do career data dropped calls dot drop NA, the drop NA method. Access equals 1, that basically means go through the columns. And then how equals all. So basically whenever all of the data is null, drop that column. So we want to get rid of that as well. And then let's go ahead and do the length again. Whoops, spelled columns wrong. $19. So it looks like we actually dropped 2 columns. So that's awesome. There were 2 columns where every value was null, and we dropped those 2 columns. Cool. So as you can see, we've dropped about, not really 25%, we've dropped about 33% of our data in columns. And this will make our data much easier to work with. Now, instead of working with 30 columns, of which 11 told us basically nothing, we can work with just 19 columns, of which there's probably more useful information there. As a bit of a side note, variability in individual columns is what gives machine learning algorithms their predictive power. There's information in variability, and processes like principal component analysis, which is beyond the scope of this course, rely on this variability to eke out information about a data set. So that's just like a little bit of a small side note or tidbit for you. the information that a machine learning algorithm is able to like get out of a data set oftentimes lies in the variability of individual columns. And if you think about it, that makes sense. If the values are not changing in individual columns, then it's going to be difficult to see what value within a variable correlates to, what the outcome we're looking for. All right, so step 1, we went ahead and got rid of any data that doesn't give us any information. Step 2, we want to work on the data types of data that we're working with. So drink my water there. So we want to verify that our data types to ensure that they've been recognized by Python as the right data types. While there are dozens of different types of data, at the core for our purposes, we only need to worry about 3: numerical data, date data, and string data. So numerical data, these are essentially numerical values where you can that you can perform math on. The math distinction is important. So for example, the American Postal Code System, also known as zip codes, is a 5-digit number, but shouldn't be encoded as a numerical value because you can't perform any math on a zip code. So like 90210 is no higher or lower of a zip code than 01931. And additionally, zip codes in the northeastern United States, especially those in Maine, they have leading zeros in them, which will be removed if you code them in as a numerical data type. So for example, if you have a CSV that says 01931, when you import it into pandas, it'll only import 1931, which is why you want to make sure that you encode these as string data types and not numerical data types. So that's one way of like remembering that not all numerical data types are, not all like numbers are numerical data types. You have to be able to perform math on it, and it can't have any leading zeros. Dates. So to quote myself over here, formatting dates is the bane of any data scientist's existence. And this is because dates can be formatted in so many different ways. And they're so non-standard in how they work, basically. So dates are a way that we can measure temporal or time-based data. It's key that you understand your data well enough to understand what format your date data is in, and use the features of Python to parse out these dates. So for example, like if you live in the United States, we follow the month, day, year format. But basically, everyone else in the world follows day, month, year. And a lot of SQL databases will follow year, month, day, which makes a lot of sense because you can string sort year, month, day accurately in a way that you can't do day, month, year. So I prefer to have my dates in a year, month, day format, which is what you see over here, 2020-05-23. That's a year, month, day format because it allows you to easily sort your data no matter what format it's in. And then string data, and this is a catch-all data type for anything that can't quite fit into the other 2 data types, and it refers to data that's stored as text. So to test out the data types, we'll use the dtypes method. So let's go ahead and take our data over here, career data dropped calls.dtypes. And we'll hit Shift Enter, and you can see the different data types that Python identifies each of our columns in. So unique ID, for example, is an object. Crawl timestamp, so it looks like our timestamp is actually identified as an object and not a date. So most things are the object data type, and the object data type is basically a string data type. So let's take a look at the salary offered column. It seems to be formatted as a string with $signs and commas. So let me actually take a look at it. So we take a look at it. So you would, looking at this, right? You look at salary offered and you're like, salary offered should probably be a numerical data type because, you can perform math on salaries. So as you can see, it looks like we have a $sign and commas in here. And that's probably what's messing up our Python's understanding of what this data is. So we'll go ahead and correct that. So we can use these functions over here to convert it to a numerical data type. So again, remember, we're going to be doing that same thing I said where we're going to create a new, because we're going to be doing a new transformation on our data entirely. Career data dtype change equals career data dropped calls dot copy. And then what we're going to do is we're going to go to salary offer. We're going to take the salary offered column and we're going to apply a lambda function, x.replace the $sign with nothing, and then replace any commas with nothing as well. And then this is the important part over here, dot as type float. Floats are basically decimal numbers instead of ints, which are just integers, whole numbers basically. So let me do that and then take a look at it. Oh, I need to set it equal to. All right, so let's run this again. And you can see we've converted all of our dollar signs into float types, and our machine learning algorithm will be able to better identify these and understand that these are numbers. Okay, so now let's focus on the dates and a column that isn't a string but should be one. Towards the end of the data set, you'll see a postal code column. So let us take this, and then we'll do a dot columns method. And you'll see postal code over here. And if we do .dtypes, it's probably encoded as an int64. Again, remember that postal codes are oftentimes read in as integers when they should be read in as strings. So in the United States, which is the region that this data set covers, postal codes, more commonly known as zip codes, are 5-digit numbers ranging from quintuple 0 to quintuple 9. And they're generally grouped geographically and can even have leading zeros in the Northeast. Many of Boston's zip codes have leading zeros. When Python reads in something as a numerical data type, it will drop leading zeros that aren't preceded by a decimal place. For this reason, plus the fact that you can't perform math on a zip code, zip codes, although being composed entirely of integers, should be recognized as strings. In order to ensure that the data is imported correctly, we will actually add the information to convert postal code to a string in this statement where we import our CSV. So we have to go all the way back to the beginning and actually import our CSV correctly. So we're going to change, we're going to add this D type and add a dictionary that says postal code is a string. That way, in case we dropped any leading zeros, we can make sure to bring that in. And you'll do this quite a bit where you might go back and edit some stuff, because the reason I do this afterwards is because I want to go through and get rid of any data I don't need first. That way I'm not converting a bunch of data into the right format and not end up needing it at all. That's why I just import the data as it is, and then I change it when I need to. So you can see over here, we just went back to career data, and we added this D-type parameter over here equals this dictionary, postal code string. So remember, this is all part of the data cleaning process, and then I'm going to click this run notebook button over here. There we go. And you can see postal code is now an object, which is exactly what we were looking for. And that way we can also guarantee that it reads in leading zeros when it's actually reading in the CSV. Another way to solve this problem is to save things as pickle files, so .pkl files, where what happens is it'll save a pandas data frame as a pandas data frame. So it'll store all the data types and everything. And actually I've started to start saving my files as PKLs and not CSVs anymore, only because it keeps all of the metadata of the file that I need to actually that might actually be important. Okay, next we'll look at parsing dates. So date formatting can be the bane of any data scientist's existence because they can be very ambiguous and based on where you live and where your data set is from. So I've worked with European data, and obviously European data, dates are formatted differently than the US, but you have to be very clear about how your dates are formatted whenever you're formatting your date information. So this is something to be very cognizant about. And we can parse dates on import using the parse dates argument in the read CSV method, but I'll be using a different method here since we have dates in a couple of different formats. So let's take a quick look at the formats our date columns have adopted. So we're going to copy this list of date columns that I have. I think... okay, I thought by pressing, oh, cool, it did. Okay, so I pressed format code, and it actually formatted the code, so it's a lot nicer. We can read all of the columns all at once. All right, so You can see this is like a complete date time format with a time zone. So this plus quadruple zero is like a time zone stamp. So you know what time zone that the data came in. And you'll see a lot of time stamp data is like that. Basically, whenever like whenever data is inserted into databases, oftentimes they'll add a timestamp. Valid through, this is just normal date format. But you'll see this format over here, it looks like they've dropped any delimiters. This one uses periods as delimiters. And these two are copies of the previous two, it looks like. So normally you would use the parse dates function in the read CSV method, but because our dates are all coming in different formats, we'll want to address each of these formats differently. So I already know pandas can't automatically determine which of these formats to use, so we'll just go straight and handle it manually. Yeah, so let's go ahead and copy this code down here. And let's run it. All right. Sweet. So it looks like that formatted correctly. And then post date, year, month, day. Come on. Let's see if I can. There we go. I think this is it. No, it's different. And you can see this got converted as well. So I only converted 2 of them, and I'll let you practice on the period one, the one with the little periods inside it. And you can see basically what we did over here is we did pd.toDateTime, and we surrounded the actual method we wanted, like the method of the format we want to use. So for this crawl timestamp, that's in a very normal format. So we can just tell Python to try and figure out how to format that, and it figured it out well. But for this post date YYY format, which if you remember was this column over here, where like there was no delimiters, it needs to have the format specified to it. And that's why, whoops, let's go down a little bit. Oh, not here. Over here, I specified the format. I said percentage Y, which is the full year, the four-digit year. I think a lowercase y is a 2-digit year, like so 95 instead of 1995. Percentage lowercase m, which is the 2-digit month name. So like May is 05, December is 12. And then percentage D, which is the 2-digit day name, which is like, like the first is 02, and then the 20th would be 20. So by specifying this format over here, when Python can't figure it out by itself, I'm telling it, okay, this is the format that the date is in. Here's how you format it. And this is what I mean by like dates are kind of the bane of a data scientist's existence. Like there are all these different formats that data can come in, or that dates can come in, and you have to be ready to tackle all of them. If you want to get more information on how to actually use this function, be sure to check out the pandas documentation. Very well done. Pandas.toDateTime is a specific function you're looking for. And if you want to know how to format things, I think they link it over here. Here it is, yeah. Stirp time and stirp time format codes. And you'll see, for example, percentage Y with the century. So like a capital Y will show you the century, and a lowercase y will not show you the century. So that is editing date data types. And I'll let you do the period one yourself as practice, the one with the period inside it. All right, so let's go to the next section. And now that we have all of our data in the correct date format, now that we have all of our data in the correct data formats, data types basically, we'll want to deal with missing data. You can make an entire chapter just dealing with missing data. So for the sake of brevity, we'll just go over some of the basic techniques. And I'll release a video with more advanced techniques in the future, because there are a bunch of really advanced techniques you can use to deal with missing data. But we'll just go over the really basic ones right now. your machine learning algorithm, they don't deal with missing data very well. So you want to specify what is going on with missing data. That way your machine learning algorithm can learn appropriately. So again, remember, it's a room of 5-year-olds. They can't extrapolate. They can't figure out things on their own, which is why you have to kind of specify everything for the machine learning algorithm and kind of allow and provide it with the right learning environment for it to learn stuff by itself. So first we'll need to determine the percentage of missing values in our data set per column. Missing data can come in many forms. So let's create a list of missing data values and then look for columns with the most missing data values as a percentage of all of their values. So I'm going to copy this over here. And you'll see what I did over here is I created a list of missing values, like common missing values. np.nan, so this is the common NumPy, this is the null value within NumPy, and when you see a null value, this is normally what it is. It's an np.nan, or not a number value. A blank can also be a null value, or something with just a space can also be a null value, or the none variable can also, or the none value can also be like a null value. So career data underscore dtype underscore change dot is in missing values dot mean dot sort values ascending equals false times 100. This function will give us, or this not function, this little bit of code will give us the percentage of values per column that are missing. So you'll see inferred salary to, inferred salary from, over 87% of the data is missing there. Inferred city, 6% of the data is missing, and job type, 5% of the data is missing. So it looks like for some columns, we have a bunch of missing values. If you have 87% of your data missing for these columns, there's really not much we can do about this. And our data set most likely won't be able to glean a lot of information from this. Now, that being said, missing data could also just mean that like it's supposed to be missing, as in like there was no value here, and that's what it's supposed to be. For the sake of argument over here, we'll just say that it's inferred salary to and from. Missing data just means it's bad data, and we just don't have it, so we should probably get rid of it. So when you can't find a way to bring in more data, one solution to a bunch of missing data is to just drop it. That's the first technique we'll be using. So let's drop any columns where more than 86% of the data is missing. So we're going to copy this code over here. So we're going to create another columns to drop variable, and it'll be career data dtype change dot is in missing values dot mean career data, and then we're getting any column where the percentage is above 0.86, so above 86% basically. And then we're creating a copy. Again, this is a new data cleaning step, so we're going to call it career data missing values and set that to be a copy of career data dtype change. And we are going to drop those columns. So let's go ahead and run it. And we should have 17 columns to work with right now. So whoops. I will say that's something that's a little bit weird in that if you hit delete at the beginning of a block, it'll like go to the previous block, which I guess might make sense if you're used to it. But every block, I kind of just expect it to be like a different entity, kind of. And we have our 17 over here. Perfect. So we dropped 2 columns. Those 2 columns that were 86% null. We don't want to use them because there's no predictive power in them. And look at that. We've gone from 30 columns to 17 columns. This is why the whole data cleaning process is so important. You know, you're looking for these things that you want to provide your machine learning algorithm with the best learning environment. And that means getting rid of a lot of data that just isn't necessary. All right. You kind of need to think about your machine learning algorithm as this thing that needs to be nurtured and provided the best environment to succeed in. And that's why we want to do as much as we do over here. So awesome. We've dealt with missing data, or sorry, that's one method to deal with missing data. So missing data is another aspect of data cleaning. And we've handled 2 columns by just dropping data from it. The next, or by just dropping the column. You could also drop individual rows, but I don't want to drop 86% of our rows of data because more data is generally better. So the next thing we can do is we can do this thing called imputation. And when you have too much missing data, as in the case of the columns we just dropped, you might not have an option to keep said data. But when less data is missing, there are a couple of tricks you can use in order to keep a larger data set, basically keep those columns in your data. In this course, we'll go over the most basic one, imputation. Imputation basically is simply the process of replacing missing values in a data set with another value. The most common values to impute are means, medians, and modes of a column of the column in question. By doing this, you can keep the column in question while also putting a relatively good estimate of what the value would have been in place of any missing values. If we run through the following script again, we'll see that we have 3 columns with missing information. So let's focus on inferred city. Let me see, Control A, Control C. Let's actually run through that and bring it over here. Yeah, so it looks like inferred city and job type are both a bit, like they have a couple of null values inside them. Like, so 7% might be very, very doable, as we can handle that. So let's focus on the inferred city column. You'll see that we have quite a few cities in here and that this is a text-based column. So oh, whoops. Did not mean to do that. Yeah, so you'll see we have quite a few. Yeah, we have quite a few. What do you call it? Cities over here, and they seem to span the entirety of the United States. And it's a text-based column, so like because it's a text-based column, you can't really take the median or mean of it. Like you can take the median, but the median of a text-based column is oftentimes like meaningless. Like the median city over here would not make any sense. So you don't want to impute the mean and you don't want to impute the median. We actually use a more intelligent strategy in order to try and like guess what might make sense. So we're going to use the mode, but just blindly using the mode of the entire column when we can probably make a more educated guess is probably not a great idea. Remember, GIGO, garbage in, garbage out. We need to be very careful what we put into our algorithms. And it looks like we have a column called inferred state in this data set. And given that there's always a correlation between the city and state columns, we might be able to take the mode city of each state and map that over the missing values in the inferred city column. So if you think about it, taking the city that appears the most per state, the mode city, mode, remember, is the value that appears the most in a data set. That might be a more intelligent way of filling in the 6 to 7% of missing values that we have in this data set or in this column. So let's go ahead and do this. All right, so I fixed the problem in my code. So this is a new code or new piece of code we're going to be using that will basically just pick the first value amongst the modes. So you'll see what we have over here now is we have every single state followed by the city that appears most in the data set, which usually tends to be the biggest city in that state if you look at it. All right, so now that we have this dictionary of every state and the mode city, let's go ahead and map that to our inferred city column. So we do career data, missing values, inferred city. So, we do the inferred city column and we do .fill NA and then we give it this dictionary and just map it like that. So if we do that, then you'll actually see, let's see. So there's inferred city over there. Actually, I should have demonstrated this a little bit earlier. It's actually a feature in Deep Node that's pretty cool. You'll see inferred city on this earlier iteration of our data frame. Deep Node actually tells us that we have missing values over here. So Deep Node has all these features that can make the machine learning process a lot easier. You can even like integrate with GitHub and stuff like that, which I haven't used over here, but you totally could. So missing values over there, 6.8%. But if we go down here, we'll see we are at a very acceptable 0%. Whoops. Let's see. Inferred city. Yep, 0% right over there. So as you can see, that is one way to do basic imputation. So instead of so you can impute the mean, median, or mode or a different value, but you can see how we intelligently imputed the mode. We didn't just blank put in the city that appears the most, because that would make absolutely no sense. We put in the city that appears the most given that we have a state column. That's a much more intelligent way of doing it. And that's kind of what you want to do. You want to like think through what's the most logical way for you to impute your data and what's the most logical way for you to clean your data. So that's something that is really important in the machine learning process. You don't want to just blindly do things and blindly just execute step after step. You want to really think about, okay, how does this actually work with our algorithm later down the line? So the next thing we need to do is we need to select a target column. And if we have a problem where we'll be using supervised learning, then we'll want to split out our target variables from our predictor variables. And this is relatively simple, as we'll just create a new series with our target variable and call it y, and then set all other columns in our data frame to equal x. And actually, it's usually a capital X. So convention dictates it's a capital X. And you want to follow convention if you can, because other people are going to be reading your code as well. And code, as I always say, is written more than it's read. Or sorry, is read more than it's written. So it's very important that you use convention when you can. Excuse me. Next, we have data encoding. So many machine learning algorithms require all of their inputs and outputs to be numeric. So how do we use categorical data if all data has to be numeric? Well, we systematically turn those categorical variables into numeric values through a process called encoding. So there are a couple of different types of encoding. We'll go over label encoding first. So label encoding refers to the practice of simply assigning a random number to each category in a column. This is the simplest form of encoding, but comes with a major drawback in that it imposes ordinality on your data. So say you have 3 cities in the column and you encode them like so, like Houston is 1, Dallas is 2, Austin is 3. When your machine learning algorithm sees this, it might assume that there's some relation between the numbers in this column that doesn't actually exist. Houston is better than Austin because it's number 1. Dallas is 2 times Houston because it's number 2. And it's for this reason that we'll generally want to avoid label encoding. For practice, let's try and implement this on our inferred state column. Label encoding is sometimes useful, but you'll generally want to avoid it in favor of one-hot encoding, which we'll go over in a minute. So if you see over here, career data encoded equals career data missing values.copy. So, again, we're creating a new copy of the data frame. And from sklearn, we're importing. So sklearn is scikit-learn, and it's the standard machine learning library for Python. And it's what we almost always use for all like machine learning in Python. And they have a lot of, so it's kind of like the end-to-end thing. Like there's a lot of functions inside sklearn that help with other aspects of machine learning, not just the actual like modeling itself. So we're going to create a label encoding object. So it'll be called LA. Actually, you know what? Let's actually, the normal way we do this is actually like this. Whoops. This is slightly non-standard behavior. There we go. So I'm writing the exact same thing. I'm just writing it a different way. This is actually how we normally import sklearn stuff. So you go sklearn, you go module, and then you import the specific method you need. So LE equals label encoder. We're creating a label encoder object. And then career data encoded inferred state. So this column is equal to le.fitTransform. So we're fitting it to this label encoder object, and we're fitting it and transforming it. So fitting it means learn the pattern from this data. So basically encode it and memorize that within this object over here. And then transforming it means actually like turn it into what we want it to be. So le.fitTransform career data encoded inferred state. And let me actually reveal this column. And if we run this, then you'll see everything got converted from a number 1 through 50. So that is a label encoded column. And let's go ahead and change the Notion notes to copy this over here. There we go. And that's label encoding. Next, we'll be going over one-hot encoding, which is usually what we end up doing instead. So as you probably guessed, or as you definitely saw, label encoding does impose some ordinality on your data, which may not be the desired effect. So one-hot encoding avoids the above problem by creating a new column for every category in a column and then assigning each row a 1 or 0, depending on whether that value is present or not. That might be a little bit easier to understand. So let's say we have this table over here. Our indexes are 1 through 5, and city, Dallas, Houston, Dallas, Dallas, Austin. So if you were to one-hot encode this table over here, where I think, let us call this the header column. There we go. And let's do the same thing over here. So if you were to one-hot encode this column over here, the city column, then you'd get something like this. You'd have a new column created called City Dallas, one called City Houston, and one called City Austin. And you'll see the first value is Dallas, right? The first row on index 1, the row it's Dallas. Then you'll see City Dallas is 1, and the other 2 are 0. And the second one is Houston, right? So that gets converted to City Houston is 1, and the other 2 are 0. And so on and so forth. That's called one-hot encoding. And as you can see, we've now expressed the city column in 3 different columns called dummy variables, 1 for each value of a city. This helps us avoid the ordinality problem that we had earlier. The problem with one-hot encoding, though, is that if we use this on a column with a lot of categories, say it has 10,000 categories inside it, it can lead to an explosion of features. You know, each of these is now a new feature, right? So it can lead to an explosion of features, which can really slow down the processing time and make running a machine learning algorithm for even basic operations on your data very hard. And we can perform this operation on our inferred state data now by using the getDummies method from Pandas. So a lot of people will use sklearn to do this, but Pandas has a great method called getDummies, which we can use that'll just do this for us, and it's a lot easier. All right, so run. And as you can see, we've created new states. Now, you know, obviously we changed the inferred state column to be a bunch of numbers, but this would normally be, you know what, I can probably actually backtrack a little bit and show you guys what it actually looks like. Yeah, let's copy this over here. Again, the benefit of having multiple variables, backtracking is really easy. I don't have to run all this code again. So you'll see state Alabama, state Alaska, state Arizona. We created a bunch of new columns for every state in our data set. So that's how you use the getDummies method from Pandas in order to create a bunch of dummy columns. Now, we need to talk about something called the dummy variable trap. And another problem with one-hot encoding outside of the feature explosion problem is that the dummy is a dummy variable trap. And when your machine learning algorithm looks through the 3 city columns, so let's go back to the example of where we just had Dallas, Austin, and Houston. When it looks through the 3 city columns that have been created, if it reads any 2 of them, it'll know what the value is in the third. So for example, if Dallas and Houston are both 0, then Austin's going to be 1. This ability for certain columns to predict the values in another column is called multicollinearity and is a big no-no in the world of machine learning. Your algorithm is supposed to predict the value of your column or cluster your data using your predictor variables. If columns are self-predicting, then the algorithm won't be able to separate out the desired pattern from an accidental one you've created in your dummy variables. And the simple solution to this problem is to just drop one of the dummy variables you created. And for the above example, you can use the drop first parameter to remove the first dummy variable that's created. So let's go ahead and try this again. And let's make sure to replace this. Woo. I think Alabama will get removed. Yep, and as you can see, Alabama's been removed. We go straight to Alaska. And this helps prevent a multicollinearity issue, which we'll go over very briefly a little bit later in the course. But multicollinearity is definitely something you want to avoid when you're cleaning your data for machine learning. All right. So one more thing I just want to bring your attention to, we're not going to go over it over here. Hash encoding is one method to help deal with the explosion of features that can result from one-hot encoding, and it's out of scope for this course. So I'll let you read into this or look it up yourself, but hash encoding is definitely something that on your own time you should look up, but it's a little bit out of scope for this course. So let's take a step back and see what are we doing over here and how does it relate to everything. So if you remember the CRISP-DM lifecycle over here, right? We skipped over these two steps because this is a completely separate video. And now we're in the data preparation phase before we go to modeling. So chapter 5, which is what we're on right now, we're talking about data preparation. And I'm going over the basic steps right now that are common amongst many data sets whenever you are about to execute on a machine learning algorithm. So we've gone over a couple of concepts so far. If we go back to the table of contents over here, we have talked about initial setup and import, the basic data format your data needs to be in. Remember, one column for every variable, one row for every observation. We removed columns with only one unique value. Remember, if there's only one unique value, there's no predictive power in that. And, what's the point then? Data types, we have settled on 3 different data types: dates, strings, and numerics. And, we talked about the difference between numerics that are, a bunch of numbered data and numerics that are actually like numerical data. Parsing dates, basically turning date data into date data and making sure that it's like recognized as a date by Python. Missing data, where we deal with values that are just missing. And, for one where like 86% of values are missing, we just drop that column entirely because there's not much we can do about that. But if only 6% of the data is missing, then we decide to use imputation, where we pick the mode. It could be the mean or median, but in this case, it was the mode per state. That way we get a reasonable answer as to what that city column or that city the city observation in the city column might have been. Selecting the target column, which, you just separate out your Y and your X. Your Y, what you're trying to predict, is going to be your target column, and then everything else is your X. And data encoding, where we basically take categorical data, we take string data, and we convert it to some numerical format. And the reason we do that is that way a lot of machine learning algorithms require that the data comes in a numerical format. And that is like well, actually, no, we still have to go over scaling and normalization. But next we'll be going over multicollinearity, feature engineering, scaling and normalization, and train test split. So we're almost done with the data cleaning aspect of the course over here. So actually, I'm going to rename this chapter Data Cleaning and Environment Setup. I feel like that's actually what we want to call it. And then we want to go to multicollinearity. All right. So multicollinearity refers to multiple features being highly correlated to one another in a model. Like we mentioned earlier, this is something that we're trying to avoid because it makes it difficult for the model to determine which variable is actually affecting the target variable. And there are multiple ways, there are a couple of ways that we can limit multicollinearity using VIF, or variance inflation factor. That's one of the most popular ways. There is a great resource over here. I'm not sure why, let's see, advanced, go anyways. This is a tremendous website, Penn State, the College of Science. They have a great article on, I think this is actually like a textbook, basically, an electronic textbook. And they have a great article over here on multicollinearity and using VIF. So I highly recommend reading this on your own time. Again, multicollinearity is something that's a little bit more advanced in data cleaning for machine learning. So I would learn all the other stuff first and then come back and deal with multicollinearity. But it's definitely something to watch out for. So I'm leaving that outside of this course to, limit how much time we actually spend here. But definitely something you want to take a look at. Next, we can talk about feature engineering. So feature engineering is a term you'll hear thrown around a lot and basically refers to the process of combining domain knowledge with mathematical knowledge to transform features in your data set to be more informative. A great example would be if you were working with a data set of car data where you're trying to predict the price of a car based on some engine metrics. And you can use domain knowledge to determine what displacement is, basically how much air is displaced by an engine, and how that's correlated to price. You could then calculate displacement for each row of data based on other information that you might have. The link below, this Kaggle over here, has code written out that explains this exact process. So this is a great Kaggle Kaggle workbook written by Ryan Holbrook, where he talks about using domain knowledge for feature engineering. Again, feature engineering, I think, is something that after you get the other basics of data cleaning done, you should start taking a look at it and see how you could use some feature engineering in your data set. And this is where the domain knowledge of like understanding your field is actually very useful in machine learning and in data science. So that is another thing that I would say is kind of beyond, it's kind of like, I wouldn't even say its own course, but it's like, it's an entire video could be made on like feature engineering because you could go so in depth in it. And remember, the point of this course is to kind of be a primer on machine learning. I want to teach you a lot, but I also want to just like make you aware of some other things because I don't believe that we could effectively get through everything in this course. Next is scaling. So we're actually not going to deal with normalization. We're just going to deal with scaling. Many machine learning algorithms won't perform well if your numerical data is all on different scales. And this is why we often want to scale our data. Scaling is a process of limiting the numerical values of a column to a predefined range, usually between 0 and 1. And if we were to scale the below table, we'd end up with this. So for example, if the values were 1, 2, or 1, 4, 5, 2, 9, if you were to scale that column, you would end up with these values over here: 0, 0.375, 0.5, 0.125, 1. And this uses a method called min-max scaling, which scales your value such that 1 represents your maximum value and 0 represents your minimum value. So let's scale our Unix timestamp column. So let's go ahead and take a look at that real fast. I think it's just called that. It might not be. Post date Unix timestamp. And for anyone not aware, a Unix timestamp is basically the number of, I believe, seconds after the year 1970, so January 1st, 1970, that a certain... And so a Unix timestamp is basically the number of seconds past the year 1970, which is, I think it's called like the Unix epoch or something like that. So it's a way of expressing dates as complete integers, basically. And so what we might want to do is we want to scale this data over here. So let's go ahead and copy this code over here. So like I mentioned earlier, a lot of machine learning like functions come from the sklearn library. So from sklearn.preprocessing, import min-max scaler, and then we're creating a copy of our data frame. We're creating a min-max scalar object, and this is the basic format you'll see with a lot of sklearn stuff, where you create an object and then you fit and transform your data based on that object. So career data scaled, we're going to scale this value over here, and we're going to fit transform it to the scalar object we created. So let's go ahead and run that. And let's go look at our Unix timestamp data. I think it's this one, right? No. Oh, yeah, here it is. Yeah, post-date Unix timestamp. And you'll see all the values got scaled to be between 0 and 1. So you'll see, again, another great feature of DeepNote, you'll see this histogram over here that represents all the values between 0 and 1. And you can see how the data is distributed. All right, so, oh, and then also one thing to understand, there is, watch out for this double bracket over here. I completely missed it. It's just a quirk of sklearn. You have to like have this double bracket over here in order for it to work properly. So just as a bit of a heads up. All right, and I think finally we need to do our train test split. So remember how I mentioned we have our training data and we have our testing data. We need to split the two. So after we've performed all of our data transformations, it's time to split our data into a training and testing data set. Remember that the training data set is what we're training our algorithms on, and we test its performance on the testing data set. The exact percentage you need to split your data set by varies depending on who you ask, but most people will say something less than 33% of your data, something less than 33% for your test data, and the rest should be your training. Remember, the more data you train on, broadly speaking, the better your algorithm will perform. But at the same time, you want to have enough test data to fully verify the performance of your algorithm. You want to make sure your test data is actually somewhat representative of all the types of data your algorithm could encounter. Like everything in machine learning, a lot of the complexity comes with making calls as to what your trade-offs will be. sklearn defaults to a 25% test size, which is what we'll use. To fully demonstrate this process, let's pretend we're trying to predict income so that our target variable is y. So, copy this. And you'll see what we do over here is we say from sklearn.model_selection, import train test split. And then we have 4 different variables, xtrain, xtest, ytrain, and ytest. And we're assigning that to the train test split. Your first argument is the x value, which is, assuming we want to predict salaries, right? We're just going to take the career data scale data and drop the salary offered column, and that'll be all of your x data. And your y data will just be the career data scaled salary offered column. And by doing that, we will get our xtrain, xtest, ytrain, and ytest data. And we have our train test split. We have our xtrain data and our ytrain data, which correlate to each other. And then we have our xtest data and our ytest data, which correlate to each other. So congratulations, that's all of chapter 5, and you have finished cleaning your data, and we can finally get to the part you've been waiting for, which is actually implementing a machine learning algorithm. I know that you were probably hoping we get to that first, but it cannot be overstated how important clean data is to a good analysis and to actually having your machine learning algorithm do what you want it to do. But now that we've gone through a lot of basic data cleaning procedures, the actual process of machine learning is a lot easier than it sounds like. So let's go ahead and get started. All right, let's start chapter 6. So again, as we mentioned earlier, we're not really going over the business understanding or data understanding too much in this course over here. We just finished chapter 5, which went over data preparation. And now let's go into modeling, which is going to be chapter 6. We'll be talking about regression and classification problems. That'll kind of be the extent of this course because that'll cover a decent amount of the machine learning that you'll do towards a beginning level. I would like to cover clustering in a future video, but I also have another series of videos where I do cover this information as well, just in case you're interested. So we will cover modeling and evaluation simultaneously because they go hand in hand, because when you model something, you need to also evaluate how it's operating in order to edit your algorithms and make them perform better. So let's go to chapter 6, regression. So remember, regression is a supervised technique for predicting a numerical variable. Today we'll be using a data set from Kaggle to try and predict the prices of cars. The data set's available to download right over here. So you'll see this data set was created by this guy named Aditya. And it is basically scraped data of used car listings, 100,000 listings, which have been separated into files corresponding to each car's manufacturer. So I think we're going to be using, we're going to be going through BMW and seeing what they're all up to. So as we always talk about, after your business and data understanding, the first step is data cleaning. So what you usually want to do is you want to go through your data, look at it, and see, okay, what data cleaning do I need to perform? So another great feature of Deep Note is that if you go to this data folder over here, and I think I have it in the car data folder, click on BMW, and you will get a very nicely formatted CSV view, which shows how different variables are distributed. You can limit your data, increase your data, and then output a JSON, a CSV, a filtered JSON. A lot of great features. Each of your variables is colored differently over here if you have a categorical variable. Each of your records, categories, each of your categories is colored differently within one categorical variable. So again, these are just useful features for anyone to have whenever they're performing data science operations, and just thought I'd share them with you guys. So let's go ahead and create a chapter 6 notebook. And let's outline the basic processes that we'll be following. So we're first going to remove columns with one unique variable, one unique value. We're going to deal with our missing data, target column. We're going to separate out the price column from everything else. Feature engineering, data encoding, scaling, and train test split. So we're going to go through this a little bit faster. That way we can get to the actual machine learning pretty quickly, since we literally just went over data cleaning. So let's first of all import our data. That's surprising. I thought I would have. Okay. So let's see, data equals pd.read CSV. Data, car data, BMW.csv. Actually, in that case, I would rather just put that over here, and then I can delete this folder. It's an unnecessary folder. And then we'll just remove this. Oh, whoops. That was not what I was supposed to do. There we go. Cool, simplifies it a little bit. And let us start off. All right, so we need to first see if there are any columns where there is only one unique value. So we'll use what we did last time. Data.nUnique. And it looks like every single column has more than one unique value in it. So we don't have to do anything this step. So that's awesome. Now let's go deal with missing data. This is one where we can look and see how much data is missing. And what we're doing over here is we're looking for isNA, and we're just summing up everything. And it looks like 0 across the board. We could always use the method we showed earlier. In fact, why don't we just do that? Keep it consistent throughout the video. Okay, so I'll go to the index, or the glossary, table of contents, sorry, table of contents. Click on missing values over here. We'll copy this. That's classification. Need to go to regression. There we go. And then we'll just switch this to, say, data. Oh, we need to import numpy as np. You should always import pandas and numpy together. People like numpy. I don't use numpy all that much. Like when I create my own code, I generally don't use numpy all that much, but other people seem to love numpy, so we should be using numpy. All right, and it looks like 0% of the data is missing on all columns. So let's copy this and let's use just the same format we used earlier. So it looks like every single row of every single column is full. Awesome job. Another step we can skip. This is a really clean data set. And I picked a clean data set on purpose. And now we need to separate out our target column. So our target column is the price column. So we're just going to do x equals data.drop. Remember the columns parameter. And we're just going to drop the price column. And y is just going to be the data price column itself. So there we go. That step is pretty simple. And again, this is a particularly clean set of data. And I picked a clean set of data on purpose because I wanted to actually get to the modeling things we just did, the data cleaning. And now we can do a little bit of feature engineering. So if you remember earlier, we talked about feature engineering and how it's essentially using domain knowledge to add or enhance the features in your data set. And I've taken the liberty of classifying every value in the model column as a car type. I'm a car guy, so this is pretty easy for me to do. And that's also why I picked BMW, because BMW is one of those luxury brands where the car types are generally easy to classify. Now, I mean, obviously some of this won't be necessarily correct. Like, so for example, the 4 Series, it is a coupe normally, but you can also get like a grand coupe. So this isn't going to be 100% accurate, but for our purposes, it works. So I created this dictionary over here where we can map every single model, so 5 Series, 6 Series, 1 Series, to a car type. And this is how we do it. So X model equals xmodel.str.strip. So you want to, so strip basically trims off any white space on either side of the column, or on either side of any string in the column. And you want to do that because a lot of CSV imports will have like an extra space inside them. Another reason that if you can avoid storing something as a CSV, you should. And then X car type, this is a new column, equals xmodel.map. And we're going to map on the car type column, the car type dictionary that I just created. And as you can see, it looks like we have a decent split over here. So 40% are coupes. Wow, okay. 33% are sedans. Cool, cool. Good stuff. BMW makes some nice cars. So as a side note, this is why I picked the BMW dataset. As a luxury automaker, they have fewer models than a company like VW. I was actually trying VW at first, but then it took, like, I spent over an hour encoding these values, or like trying to like link up values to each other. And like, and VW has so many cars they sell in Europe that they don't sell in the US. So I'm just like not familiar with them at all. But most of the models that BMW sells in Europe, they have some version of it in the US. Next, we need to encode our data. So we'll just use one hot encoding. So we're just going to copy this. pd.getDummies x, so we'll just dump the entire data frame in there, and we're going to drop first. So remember, we're going to drop first. That way we don't, we avoid the dummy variable trap. And you'll see we added a couple of columns. So, you know, year, mileage, obviously that won't change. Tax, that won't change. Model changes, transmission changes, fuel type changes, and car type changes. Next, we need to scale our data. So if you remember, sklearn.preprocessing, import min-max scalar. Scalar equals min-max scalar. And then, so we create that min-max scalar object, and then we create a data frame where we transform the entire data set into a scaled version of itself. And we do this after one hot encoding when our entire data set is all numerals, or they're all numbers. So now we have a scaled data set, and we will finally do a train test split. Split our data into a training set and a test set. So from sklearn.model-selection, import train test split, xtrain, xtest, ytrain, ytest, remember? And train test split equals x, y, and the test side is 0.25, which I don't really have to specify, but, you know, why not? All right, so congratulations. We just finished the data cleaning for chapter 6. Let's get on to the actual modeling now. So if we went a little bit fast, just go through the notes. They explain everything a little bit better than I did over here. All right, model selection regression. So in this course, I won't be going in depth as to how individual algorithms work, as I'll release separate videos where I actually talk about that, because you could spend I could spend like 20 to 30 minutes just talking about an individual algorithm. And if we're talking about like boosting algorithms or like neural networks, that's several videos altogether. And at the end of the day, the point of this course is not for you to like understand all these individual algorithms, because by the time I release this course, like some of these algorithms might be outdated and you might not use them. The point is to show you the basic framework you use to like implement machine learning in real life. And then you can go swap out different algorithms for what makes sense. So that's what we're trying to do over here. So to illustrate how different algorithms work, we'll try 3 different algorithms. We'll do a multiple linear regression, a random forest, and a boosting algorithm. So multiple linear regression is something you might have learned in Stats 101. Basically, using multiple variables, we can build a linear model that uses coefficients attached to each variable plus some constant to try and predict an outcome. A random forest algorithm is a staple of any data scientist toolbox. It basically works by creating a forest of decision trees, and which are basically, a decision tree is another machine learning algorithm. And because a random forest is an algorithm of algorithms, it's called an ensemble algorithm. And boosting is a very interesting technique that's risen to prominence over the last couple of years for its dominance of calculus competitions. They're lightweight, they're fast, and they're easy to implement. So this is versus a neural network. Like neural networks need tons of data, and they're very, very heavy, as in they like require a lot of computational power to work well. And so boosting kind of fixed those problems that like neural networks had. But essentially, boosting algorithms will start off with a simple model and then create another model that predicts from a metric that predicts, let's see, mistakes from the previous model. In the case of an XGBoost algorithm, we'll be using, no, never mind. It predicts a metric from the previous model. In the case of XGBoost, we'll be using, that metric is the error. So each iteration of the boosting algorithm predicts the errors of the previous one and uses that to correct and like get a better and better algorithm each subsequent step. So let's go ahead and implement a linear regression. So before we implement the algorithm, it'll be important for us to determine what metric we'll want to evaluate. We'll want to use to evaluate the accuracy of these models. So if you click on this link over here, you'll see that there is an entire section over here for just regression metrics. And actually, I should link this for classification metrics as well. Classification metrics, there we go. Sorry, let me just link this down here in chapter 7. There we go. Just so we have that available. All right, and as you can see, there are many different metrics that we can use. We will use the mean absolute error because it's very easy to understand. The mean absolute error, or MAE, is the average amount above or below the true value that our predictions are. And it's the mean of all of that for every single prediction out there. So it's really easy to understand, so that's why we'll use it. And before we implement an algorithm, let's go over the basic syntax we'll follow to implement most of our algorithms. Like basically all the algorithms we'll be implementing will follow this basic syntax over here. So basically, we want to import the machine learning algorithm itself, import the metric we'll be judging the machine learning algorithm on. We'll create something called a model object. We'll fit the object, the model object to our data. This is the training phase. So let me add model over there. And then we'll create predictions with our newly trained model, and then measure the efficacy of our algorithm using said metric. All right, so let's go ahead and get started. So let's go ahead and do a linear regression. So we'll first go ahead and import our actual machine learning algorithm, which is this line over here. So from sklearn.linear model, import linear regression. Next, we'll go ahead and import the metric. So from sklearn.metrics, import mean absolute error. And then let's go ahead and create our modeling object. So we'll go ahead and say linear regressor equals linear regression. So I've created a modeling object now. Now we'll fit the modeling object to our data. Super simple. This is the actual implementation of the machine learning algorithm. So we'll do linear regressor dot fit x train y train. So now we're telling the linear regressor, go ahead and try and fit yourself, try and learn, perform machine learning, whatever you want to call it, on this X train data and this Y train data. Remember, we're doing a supervised learning task over here, so you need the X train and the Y train. And then we need to create predictions on our newly trained model so that we can judge how well this model actually worked. So after we've done that, linear predictions equals linear regressor. Remember, we're using this linear regressor object, which has now been trained. Excuse me. And we're predicting X test. So X test is a bunch of X data that we can then try and predict Y test values out of. And then we'll measure the efficacy of our algorithm with our desired metric. So we'll take the mean absolute error. Remember we imported that over here from sklearn.metrics, import mean absolute error. Y test, which was the actual values. And then linear predictions are our predictions. So let's go ahead and run that. And you'll see it ran quite quickly. And basically our mean absolute error is 2,786. So I probably, and I think if I run it again, it'll get a different value. Oh, never mind. Okay, so it gets the same value. 2,786. So what this is basically saying is we're within $3,000 on average above or below in predicting the value of a car. So not amazing, but not bad. And I would kind of judge how good this is based on the mean value of a car. So let's go ahead and take Y test.mean. And the average value of a car is about $22,000. So we're a little bit, so let's see, let's do this divided by, let's see what percentage we are of it. So we're at about 12% above or below our the mean value of a car in this data set. So I wouldn't call that amazing, but that's pretty solid. That's not bad at all. That's at the end of the day, if you're within $3,000, that's, depending on your context, that may not be that bad. Let's see if we can improve this. We'll use a different algorithm next. So I hope that made a lot of sense. That I'm hoping that this format that I gave you here, this is the format you'll follow with a lot of machine learning algorithms. You'll basically be performing them like this. This is more or less what it is. Let's go ahead and do the same thing with with a random forest. So I'm just going to copy all this code over here and go over it real fast. So let me, move up. There we go. So from sklearn.ensemble import, we're importing the random forest regressor. We're using the same metric again. And we're so with the random forest regression, so we're creating this object over here, right? This n estimators over here, this is a hyperparameter. So with random forest, there are hyperparameters that are actually worth changing. And so we're going to go ahead and try and change those. So I told it to create 1,000 trees, basically. A forest of 1,000 trees. And then we're going to do that same predict function down here, the predict method. And then we're going to get the mean absolute error using y-test and random forest prediction. So we'll see how this works. So this is going to take a bit longer than linear regression. Linear regressions are very fast. And this is actually something you need to consider when you're deciding which algorithms you want to use. Some algorithms take significantly longer to train than others. And you'll talk about how like machine learning engineers and data scientists will often like, you know, when you work with a large enough model, you'll literally wait for hours to get your data out. And there we go. 1,500. That's awesome. We actually did we got a significant improvement on our algorithm by just using a different data set. Sorry, we got a significant improvement in the performance of our algorithm by using a different algorithm. So in this case, a random forest regressor performs a lot better than a linear regression. So let's go ahead and copy this. And let's see what percentage we're getting over here. I'll get that same y-test here. If I run this, you'll see we're at about a 6 to 7% error right now. So we stray 6 to 7% above or below our mean value, which is significantly better. Basically, I mean, the way I see it, if you can predict a car that's worth $22,000 on average, and these are, forget dollars, these are pounds actually. So that's even, well, no, okay, no, that is a bit worse because $1,500 is less than 1,500 pounds. But let's pretend they're dollars, you know? If you can, like, you know, predict something at 22,000, you know, pounds above or below, or like within a range of error of $1,500, like, I mean, that's not bad. Like 1,500 at 22,000 pounds, like you can negotiate that off the price of a car. Obviously not in today's market, but normally speaking, you could like negotiate that off the price of a car. So, I mean, I think that's a pretty solid estimation right there. So we cleaned our data really well. We have good data. We implemented a machine learning algorithm and we got exactly what we're looking for. Awesome. So let's go ahead and try XGBoost next. And again, like, look how easy this is. How, and you know, this is a bit of a simpler example, obviously, but to an extent, this is how simple machine learning has become in many ways. Like, people talk about it as if it's the, oh, I have to install XGBoost. Okay. So we'll do pip install XGBoost. I think that's just what it's going to be. Although machine learning can obviously be incredibly complicated, it doesn't necessarily have to be. And there are many implementations of machine learning, or there are many aspects of the machine learning process that have been made significantly easier by just the introduction of all these frameworks that kind of like modularize the process for you. So this might take a second to run. Okay, so it looks like we've installed XGBoost. Hopefully it runs relatively quickly. And it looks like our XGBoost performs even better. 1491. That is awesome. I mean, like, what are we getting now? Like, whoops. Oh, good. I thought I copied that, or I pasted that on accident. So you might be wondering, like, you know, it seems like a lot of machine learning is just getting data ready for machine learning, and that is absolutely true. Again, IBM estimates 80% of a data scientist's time is spent just getting data ready for the machine learning algorithms. And it's amazing whenever you can actually, like, when you do it well enough and you get results that, I mean, that you're happy with. I mean, I'm pretty happy with these results, considering that we've, like, done no optimization or anything. Yeah, 6.6%. I mean, you know, we're shaking and baking right now. So given that the random forest and the random forest and XGBoost were both quick to achieve and comparable to, oh, wait, no. You know what? So I think at an earlier iteration of this data set, I did that, but then I limited the data set to make it smaller because it was just taking too long. At an earlier iteration, it took me 10 minutes to train this data. I think it was because I was doing it in the evening and more people were using this service at that time. So let's go ahead and see if we can tune our random forest model to perform better. So now we're going to be doing something called hyperparameter tuning. And the hyperparameter tuning I'm using will be based off of this article, which I linked in the description below by Will Corson. And I've also linked his LinkedIn over here too. So be sure to give him a follow. He's making some pretty awesome content. And it's amazing. So, I mean, the amount of free content out there for data science is absolutely amazing. Like, you can learn 90% of what you need to for, like, you know, a data science role, like, for free online. So great job. You've officially run your first machine learning algorithms, and not just simple ones, but also advanced ones like XGBoost. Of course, the skill of a data scientist show not just in the implementation of the algorithms, but the tuning of the algorithms as well. If you remember from before, hyperparameters are the parameters that control the learning of an algorithm and basically how it gets trained. So we'll be using this excellent guide from Will Corson on hyperparameter tuning. So we'll be implementing a method called grid search CV, and actually I'm just going to run it right now because it's going to take a second to actually run. So we're going to be using a method called grid search CV, and essentially what happens is we feed it a list of hyperparameters that we want it to test out with our algorithm, and then it'll go through every single combination of those hyperparameters and run our algorithm for each one. And this process can take quite a while to complete, so I've created a significantly smaller list of hyperparameters to test than we would actually test in reality. So what we would actually do is we would test a significantly larger number of hyperparameters because, you know, this we wouldn't know if these hyperparameters were good ones. But again, it looks like it ran relatively quickly. I'm guessing it's just the time I'm using this that works a lot better. Wait. I didn't run anything yet. Yeah, I need to actually run it. So you'll see over here, we have a couple of hyperparameters. You have your n estimators, your max features, your max depth, your min sample split, min samples leaf. Each of these hyperparameters is explained inside the sklearn documentation. Again, we're not going over like individual algorithms over here, but we can test each of these hyperparameters inside the random forest and try and create a better algorithm. So there's 12 fits that we're doing. We're testing 3 folds for each of the 4 candidates, so 12 different fits that we're doing. And you see we create a random forest regressor object over here. And then we say RF random equals grid search CV, estimator equals RF. Our estimator is basically our model. Param grid equals random grid. That's basically our list of parameters. CV equals 3, verbose equals 2, and jobs equals -1. These are just random parameters that we want to like insert into our equation. You know what? I probably could have reduced CV to just 1. I'm going to do that because I think this takes 10 minutes to do normally. Oh, okay, so I can reduce it to about 2. So hopefully this runs a bit faster. And then RF random.fit equals X train, Y train. And so we're training it on each of the hyperparameters that we just above. So this is a form of hyperparameter tuning. We're tuning our hyperparameters to, or we're tuning our algorithm on different hyperparameters to see which one provides the best learning environment for our machine learning algorithm. And then we can go ahead and see which are the best hyperparameters by actually doing RF random.bestparams_. So we'll put this over here and we'll run this right after. And we will let it run. All right, looks like it finished running. I think that took about 10 minutes. I just left the room and did something else. And you'll find when you're training machine learning algorithms, you'll oftentimes just do that. You'll train it and then leave the room and go do something else. And so we did our grid search over here, and then I did RF random.bestparams, and it looks like the best parameters were to have bootstrap equals true. N estimator is the big one I'm looking for. So 1500, which is, I think that's what we used originally. So you can go ahead and put these parameters into your machine learning algorithm, your random forest regressor over here. So I don't know if I should just run this and see what happens. Oh no, N estimator should be 1500. But basically what will happen is you copy these parameters into your modeling object over here. So hopefully that's clear enough. You'll just copy them in there. And you'll get presumably your best model. Now, again, like I mentioned earlier, you would actually want to test out a much greater number of hyperparameters, but for the sake of speed over here, because you know, like the point is being made, you can just use these few hyperparameters over here. All right, so congratulations, you've run through a major part of the machine learning process. In a real life situation, you'd also want to get your results together in a presentable or deployable format, but that could happen in so many different ways. It wouldn't make sense to put that into like a course. Like you could make a PowerPoint presentation, you could deploy the model, you could create an application on the internet. There's tons of stuff you could do. So yeah, and it looks like we have a slightly better result than we did earlier. So let's go ahead and try our hands at a classification problem now. So that was regression. Awesome. It may sound like we did that pretty quickly, but again, like I said, if you do the data, the pre-steps well enough, then the actual machine learning part of it will be easier. So let's go ahead and do chapter 7. And we'll do a classification problem. So we're going to be classifying mushrooms based on toxic or edible or non-edible. So this is the data set. The data set's available from here. It's from the UCI Machine Learning Laboratory, and we have it over here. So let us go back here, and let's get rid of these. I don't need these anymore. And like we did for the classification problem, let's outline the steps we want to follow prior to actually executing them for the data cleaning process. It looks like this data set only has categorical. Oh, well, let me import the data. Okay. And then let's import NumPy too. All right, so there's our mushroom data set. And class is what we're trying to classify over here. So as you can see, it looks like our data is almost entirely categorical. Actually, I think it's entirely categorical. There's only categorical data in here. So there's a lot of stuff we won't really have to worry about. So let's go ahead and try to remove data with just with only one value inside it. So we use the same function we did earlier. So we'll go ahead and do that. And this data is small enough to where I'm not creating new copies of the variable because it's easy enough to just import separately. And let's go ahead and copy this function that we used up here. Yeah, copy. See if we can keep it consistent across the notes. And of course, these notes will also be available in a PDF format. Available on my LinkedIn, actually. If you want the PDF format, go check out my LinkedIn and follow me over there for more stuff like this. So it looks like there is no missing data. Again, a great aspect of like pre-prepared data. A lot of like you can practice your machine learning skills by using data from the UCI Machine Learning Laboratory because the data is generally pre-cleaned for you. Like that cleaning step is like done for you, which I highly recommend if you want to practice your machine learning skills. So our target column that we're trying to predict is class. It's either E or P, the value in class. So we'll go ahead and drop class from X and only have class for Y. Then we need to encode our values. So we'll do, again, dummy variables, and we'll drop the first one to avoid the dummy variable trap, same as last time. And there's no scaling involved in this because there are no numerical values, so we don't have to scale anything. And then we'll do our train test split over here. sklearn.model selection, train test split, x train x test, y train y test, train test split x, y. And let's decide what algorithms we want to use. So we want to use, let's go ahead and use a logistic regression, random forest classifier, and a boosting algorithm. I forgot which one I used over here. And as I mentioned earlier, we'll just be doing basic overviews of the algorithms here, but I'm more concerned with you learning the framework upon which you can implement these algorithms. And for this task, we'll also select the 3 algorithms. Like, I think, here's the thing. When I first learned how to do a lot of machine learning stuff, it seemed a lot more complicated than it actually is. And the reason I'm kind of going through it quickly is I also want to communicate, like, this stuff is a lot, it's at its core level, it's a lot simpler than it seems. You know, it seems very complicated, it sounds very complicated, and it can become very complicated. Like, you can, you know, create incredibly complex algorithms eventually, but at its core level, it does not have to be complex. So let's go ahead and do a logistic regression. So we're following the same format we followed earlier. So you go ahead and import your model, then your metric. We're going to be using accuracy score here. And then fit. So in this case, we are actually creating the modeling object and fitting on the same line because we don't have any hyperparameters over here to adjust. We're just doing both at the same time. And then we're going to predict on X test and then get our accuracy score. So let's go ahead and run that. And you might be wondering, why are we using logistic regression in a classification for a classification problem? So logistic regression is very like funnily named. It's actually a classification algorithm, but it's called logistic regression. Again, feel free to look it up to see like how it actually works. And it looks like we are classifying with a 99% accuracy. So that's pretty solid. That means we, you know, almost perfectly classify all of our data. Random forest classifier. Again, we're following the same basic format over here. 99%. Actually, it looks like it's, wow, yeah, the exact same. Yeah, I think I did it correctly. Yeah, looks like it's about the exact same. Cool. Very, very accurate algorithm. And then let me run this first. And so LightGBM, or light gradient boosting model, is a gradient boosting model created by Microsoft, and is generally considered to be lighter and faster than XGBoost. And if you're concerned with learning more about LightGBM, be sure to check out this excellent notebook created by this guy Prashant, 111, where he actually like explains in depth what like LightGBM is, how it works. He actually explains the theory behind it. Again, amazing notebook. Kaggle is a wealth of knowledge, and yeah, Kaggle is like it's an absolute wealth of knowledge. So be sure to check out his workbook over there if you want to learn more about LightGBM. And it looks like we have 100% accuracy over here. That's awesome. Sweet. So we implement this algorithm the same way we've been implementing all of our algorithms, by fitting our models to the training data and then predicting the classes using our newly fitted model. Very simple. And we have 100% accuracy over here. Again, these gradient boosting models are quite amazing. So here's something I want to bring up. So classification presents, for model evaluation, right? Classification presents some unique problems when it comes to evaluating algorithms. We've been using the accuracy score to judge the performance of our machine learning algorithms. And this isn't actually always the best metric to use. Intuitively, you would think that, so accuracy score is basically like how many classes were accurately predicted, right, by the algorithm. And you would think that that makes sense. But and in this data set where we have a 50-50 split between our classes, that probably works out quite well. So if you go down to class over here, you'll see there's like a 50-50 split over here. But what happens when like you have cancer diagnoses and 99% of people say don't have cancer, but 1% do? If your algorithm predicts that no one has cancer, then your algorithm is 99% correct, or it's 99% accurate. And that sounds really good, but what happened is you're really missing the 1% that actually really matters. And that's why we want to, accuracy score is not necessarily the best measure of, you know, how good your algorithm actually is. For the data set we just use, it's quite good, but for other data sets, it might not be quite as good. So here's a great article on like measures you can use to measure the efficacy of your machine learning algorithm, but it doesn't have any code to actually implement any of it. One of the best things to use on a classification problem is something called a confusion matrix, where basically you have a matrix like this, right, where n equals the total number of values that you have to predict. and the predicted values are on the top, and the predicted and the actual values are on the bottom. You want this main diagonal to have as many values in it as possible. So how many times was no predicted? How many times is yes predicted? And of those no predicted, how many were actually no and how many were actually yes? And how many of the yes predicted were actually no and how many were actually yes? So basically, you want the predicted no and the actual no to be as high as possible. And you want the predicted yes and the actual yes to be as high as possible. That basically means your algorithm is truly accurate. And this is a way you can see how all the predictions in your data actually work together. And there's a great Medium article over here where this guy Dennis T has an entire function where he creates a colorful colorful confusion matrix in the form of a function that you can just use. So I'm going to copy this over here. I've modified it slightly for our purposes, and I can just run that, and you'll see what it does is it'll create a very clean heat map. That is our confusion. I have to actually okay, I have to actually run it. Okay. So I can do it like this. Okay, so confusion, matrix plotter, and then predictions. LightGBM predictions. And then we want our y-test to be here. And then we will run this. And you can see true negative, false negative. And it looks like, so we saw 1, right? 100% to be our accuracy, but it looks like that value is rounded. And it actually looks like we have 2 false positives. So again, the confusion matrix makes it super obvious what's going on over here. You have the number of true negatives and the percentage, and the number of true positives and the percentage. And again, because this data set is so evenly balanced, we can use the accuracy measure, and that's probably a decent way to actually run this to judge the accuracy of this data set. But if we were using a different data set, we may not want to do that. And so that's why a confusion matrix is really useful. So you can see this main diagonal here has the vast majority of the values. And so this is a good algorithm. This algorithm works really well. And again, that's kind of like where with the classification problem, you have, like a regression problem, you have to determine what is considered a good outcome for you. So for example, maybe we had a $1,500 MAE, mean absolute error, in the previous example of the regression problem. And for a car worth $22,000, that's not that bad at all. But say we were trying to predict the value of, I don't know, like a Gucci handbag that's worth $9,000. Well, if you're $1,500 off at that point, that's a pretty large margin you're off by. So that's where you have to determine, based on your problem statement, what is considered a good result and how do we get as close to that good result as possible. In this instance, only having 2 false positives and 0 false negatives, I'd consider that pretty good. Now, it depends. Are we actually eating these mushrooms? Maybe we are, in which case I would actually want this to be 100% accurate, but I would say this is not bad at all. Another metric we can, or kind of metric, like a graph we can use to determine to judge the value of our classification algorithm is the area under the curve. And the area under the curve is best understood by first looking at a couple of equations. So using this confusion matrix over here, we have something called the true positive rate, which is called sensitivity, the true negative rate, which is called specificity, and the false positive rate. And so the true positive rate is the number of true positives, so this box over here, divided by the number of false negatives, so this box over here, plus true positives, which is this box over here. And this is the proportion of positive data points that are correctly considered as positive out of all data points. And you don't have to memorize this stuff, but just have this somewhere in your tool belt. And that's called sensitivity. How sensitive is the algorithm? Then you have specificity, which is the same as the true positive rate except for negative values. Basically, how specific is this algorithm? So you take the true negative rate and then you add the true negative and the false positive. So true negative and false positive, you divide the two together. And then the false positive rate is the number of false positives. So this over here, divided by the number of true negatives plus false positives. And these are the misclassified negative points out of all points. Now we can plot these values one after another at different thresholds, and this is called the ROC curve, or the Receiver Operating Characteristics curve, and represents the ability of your algorithm to separate out different classes from one another. So, which at the end of the day is kind of what you want your algorithm to do. You want your classification algorithms to handle. Let's see if we... All right, so did a little bit of finagling with the code. Basically, you have to be very careful what you consider a true positive and a false positive. So this code has now been edited from the default version, which we normally use, to show the correct ROC curve, where you want your curve to, I mean, your curve will almost never look like this. We have a perfect classifier over here, so we have a bit of an odd situation, but you almost never want your curve to actually, or sorry, you want your curve to eventually like reach this, approach this shape over here. And I think I have yeah, so there's a great visualization over here of like a perfect classifier will look kind of like this. A random classifier will be a, perfect linear line from bottom to top, and better ones will reach this perfect classifier. So we have a perfect classifier, and this is the ROC curve we have right now. So I'm going to copy this code over here, and we'll go ahead and paste it in our area over here. And that is your ROC curve. So, and AUC is area under the curve, which we have 1 over here because we have a perfect classifier. And then finally, you have the F1 score, which is basically, it's the harmonic mean between precision and recall, and calculates the precision of the classifier, the number of instances accurately classified. And a higher F1 score, it means your model is performing better. So as you can see with classification, we have a couple of considerations we have to make that we didn't have to make with regression models. So as you can probably tell, classification problems have their unique challenges that are not really faced with regression problems. And if you want to study further, then look into multi-class classification problems, as this is the way you'll design algorithms the algorithms for those are designed slightly differently than the algorithms for binary classifiers, which is what we made over here. So we've reached the end of the course right now. We've gone over a ton of content. So you've gone over the basics of machine learning within our world, how different companies use machine learning, the theory behind machine learning, how to actually holistically design a machine learning algorithm using CRISP-DM, data cleaning, which took up a lot of time because there's a lot of cleaning that you normally have to do to make data work, the data to be in the format that works best with the machine learning algorithms. Then you have regression and classification. We did three different algorithms for each of the regression and the classification problem types. And we went over how to evaluate these algorithms as well. I'll be releasing more additions to this course in the future, but I hope that this provided a nice primer for you on the world of machine learning. If you liked what you saw, be sure to like the video, subscribe to my channel, please, and if you have any suggestions, leave them down in the comment section below. And my Patreon link is below too if you want to support my work in that way. But thank you guys so much for your time, and I hope you have a great day.